Right now, we're moving through a huge region of space that is about 2 billion light-years across. Scientists confirmed this in 2013, but most people are still unaware of it. We are inside the KBC void, an area of space where there is about 20% less matter than expected. Because this region is less dense, it affects how scientists measure the universe. From our position, the universe seems to be expanding faster than in other places, which challenges some basic scientific models. How could a civilization develop in such a low-density region without noticing it? What are the implications for our understanding of the universe? In this video, we'll uncover how this discovery reshaped modern cosmology, why most of space is nearly empty, and what it means for us to live so far from the universe's denser regions. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. The KBC void is a vast cosmic desert that surrounds everything we call home, and it may be quietly bending our view of the entire universe without us realizing it. This is not a distant or abstract idea. It is the space we live in, the environment through which all our observations must pass, and it is far emptier than scientists ever expected. The first clear warning sign appeared during a massive galaxy count. In the year 2013, astronomers carried out an enormous survey that examined more than 35,000 galaxies. Wherever they looked, in every direction of the sky, something strange kept showing up. The numbers did not add up. About 20% of the galaxies that should have been there were simply missing. This was not a tiny error or a brief statistical accident. The shortage spread across an enormous region of space almost 1 billion light-years wide. According to standard ideas about how the universe is built, many galaxies should not just vanish on such huge scales. Yet the evidence was unmistakable. To be sure they were not being fooled, scientists checked the result in every way possible. They combined observations using visible light, measured galaxy distances through redshift data, and used infrared scans to search for galaxies hidden behind dust. They even looked for faint, obscured objects that normal telescopes might miss. Every method told the same story. The space around us contains far less matter than expected. This enormous underfilled region was eventually named the KBC void, after the three scientists who confirmed it: Ryan Keenan, Amy Barger, and Len Cowie. The data revealed something astonishing. Inside this region, the average amount of matter is only about 80% of what is considered normal. On human scales, that difference might not sound dramatic, but on cosmic scales it is enormous. A 20% drop in matter means weaker gravity pulling everything together. It means galaxies grow more slowly, large structures struggle to form, and space itself expands faster in this region than elsewhere. Computer models show that a void this large should be incredibly rare, with odds far smaller than 1 chance in 1,000 under standard theories. And yet, here we are, living right inside it. What makes this even more unsettling is our position. Our own galaxy sits close to the centre of this vast hollow, roughly between 200 million and 400 million light-years from its middle. The void itself stretches nearly 1 billion light-years in every direction, making it one of the largest structures of its kind ever discovered. This is not empty space in the usual sense. It still contains matter, but that matter is spread incredibly thin. If a typical region of the universe might contain 10 galaxies in a given volume, this region might contain only 2. Those galaxies are scattered far apart like isolated islands floating in a dark, silent ocean. Because there is less gas and less dark matter, gravity is weaker here. Galaxy clusters are fewer, stars form more slowly, and the large-scale pull that shapes the universe is diminished. In such an environment, dark energy takes over. Gravity cannot counterbalance it the way it does in denser regions like cosmic walls and filaments. This is not just a theoretical idea. Observations show that voids expand faster than the universe on average. Over time, they push outward, sharpening their edges and making their interiors even emptier. The KBC void follows this exact pattern. Galaxies near the edges of this vast hollow are already moving away faster than the normal expansion of the universe would predict. Our own galaxy is part of that motion. It drifts outward at roughly 600,000 miles per hour, pulled by the stronger gravity of denser regions beyond the void. This speed can be measured, and it matches precisely what scientists expect when a galaxy sits inside a massive underdense region. Our location is not random, and it is not harmless. It affects every observation we make, from how we measure exploding stars to how we interpret ancient background radiation left over from the early universe. We are not viewing the cosmos from a neutral average position. We are looking out from inside a cosmic hollow, and that changes everything we see. The discovery of the KBC void did not rely on a single telescope or one lucky observation. It emerged from agreement across many independent surveys. Astronomers first noticed the missing galaxies in wide-field redshift maps. Then radio surveys confirmed the same pattern by tracking neutral hydrogen across hundreds of millions of light-years. Infrared observations ruled out the idea that dust was hiding distant galaxies from view. No matter how scientists looked, the results stayed the same. The space around us contains about 20% less matter than it should. The shape of this region appeared roughly spherical, with our galaxy sitting close to its centre. That combination of size, shape and position made it nearly impossible to dismiss as coincidence. Next came the simulations. When cosmologists tried to recreate the universe using standard lambda cold dark matter physics, voids this large almost never appeared. To produce something like the KBC void, the early universe would have needed extremely unusual starting conditions, something closer to a 10 sigma deviation from the average density. That level of rarity is so extreme that many simulations never generate such a structure at all. And yet, the real sky showed exactly that. The surveys lined up too cleanly to ignore. A genuine, massive, underdense basin existed, and we were living inside it. This realization forced scientists to confront a deeply held assumption in cosmology, that on large enough scales, the universe is uniform and our location within it is typical. If that assumption breaks down, then many of our measurements may not describe the universe as a whole, they may only describe our local neighbourhood. What began as a technical effort to map galaxies had uncovered a structure that standard theory struggles to explain. It marked the moment when a quiet anomaly turned into a serious problem for modern astrophysics, and it opened a cosmological headache that has yet to be resolved. From a purely statistical point of view, a hollow as large as the KBC void should almost never exist. To create something this big, the early universe would have needed extremely strange starting conditions. Scientists describe it as something close to a 10 sigma drop from the average density, which is an event so rare that many computer simulations never produce anything like it at all. In theory, you can run countless virtual universes and never see a hollow this deep and this wide form even once. And yet, when astronomers looked at the real sky, the evidence refused to go away. Different surveys, carried out in different ways, all pointed to the same conclusion with surprising clarity. There really was a vast region with far less matter than expected, and we were sitting right inside it. That realization was deeply unsettling. It forced scientists to question one of the most important assumptions in cosmology, the idea that if you zoom out far enough, the universe looks the same everywhere, and that our location is not special. This assumption makes modern cosmology possible, because it allows researchers to treat local measurements as fair samples of the whole universe. But if that assumption breaks down, then measurements made from inside a giant hollow may not tell the full story. They may only describe our immediate surroundings. What began as a careful project to map galaxies quietly exposed a structure that standard theories struggle to explain. Instead of closing a chapter, it opened a long-lasting problem that cosmologists are still wrestling with. According to the standard model of the universe, a void as large as the KBC should be almost impossible to form. Simulations show that the odds of creating a hollow this deep and roughly 1 billion light-years across through random fluctuations are less than 1 chance in 1,000. Most simulated universes are filled with many small empty regions and a few medium-sized ones, but almost none reach anything close to this scale. That extreme rarity is exactly what makes the discovery so disruptive. If our cosmic neighbourhood really is this unusual, then either we happen to live in an incredibly unlikely place, or the models used to describe how the universe grew are missing something important. Neither option is comfortable for scientists. The size of the KBC void is not just slightly above average, it goes far beyond what is normally expected, even at the edges of probability. In simulations, empty regions usually span a few 100 million light-years. Stretching to about 2 billion light-years requires truly exceptional conditions in the early universe. A structure of that size cannot help but influence everything around it. Large voids are not like simple empty boxes carved out of space. They interact with nearby regions, changing the speeds of galaxies, bending the paths of light, and altering how far space appears to expand locally. The bigger the hollow, the stronger these effects become. What makes the KBC void especially important is its location. It sits right where we make many of the observations used to measure and fine-tune the universe's expansion rate. If we lived in a more ordinary region, our data might look very different. Instead, we're observing the cosmos from inside an extreme outlier. This is why the discovery did not remain a small technical detail buried in research papers. It became a central piece of one of the most important scientific debates of the past decade. The KBC void does more than raise eyebrows. It directly challenges one of cosmology's core principles, that on very large scales, the universe is roughly the same in all directions and in all places. This idea, known as homogeneity and isotropy, is what allows scientists to describe the universe with relatively simple equations. A structure this enormous pushes that principle to its breaking point. In most simulations, differences in density smooth out beyond a few 100 million light-years. The KBC void stretches nearly 3 times farther than that, making it one of the most extreme local environments ever measured. Its depth adds even more tension. The region is about 20% less dense than average, which is not a small difference. If our location is truly this unusual, then every cosmic measurement we make has to be handled with care. Distances calculated from the speeds of nearby galaxies, estimates of how fast space is expanding, and even conclusions about the age of the universe could all be slightly distorted. The numbers themselves might not be wrong, but they might be local, shaped by where we happen to be standing in the cosmos. This is where the issue stops being just about statistics and becomes a deeper theoretical problem. When a structure is too large to be common, but too consistent to dismiss, theory has to bend. Either the KBC void is a rare cosmic accident, or our understanding of how the universe formed and evolved is incomplete. That is why this enormous hollow sits at the heart of debates about cosmic expansion. It touches not only galaxy surveys, but the very foundation of how we understand the universe's shape, behaviour and history. The KBC void also offers a possible clue to one of the biggest crises in modern cosmology, the Hubble tension. This tension comes from a disagreement between 2 very precise ways of measuring how fast the universe is expanding. One method looks back to the early universe, using the faint glow of the cosmic microwave background and detailed models of the universe's first moments. That approach gives an expansion rate of about 67 kilometers per second per megaparsec. The other method looks nearby, using exploding stars called supernovae to measure distances, and it gives a higher value of about 73. Both measurements are extremely careful and precise. In theory, they should agree, but they do not. They differ by roughly 9%. If our galaxy lies inside a massive underdense basin, that mismatch suddenly makes sense. In a region where there is less matter, gravity is weaker. With less gravitational pull slowing things down, galaxies drift outwards slightly faster than average. Light travelling through such a region is bent and delayed less than usual, and the local expansion rate appears higher than it would in a denser area. This is not just a guess. When scientists simulate how a void of this size would affect the motion of nearby galaxies, the extra outward speed they calculate almost perfectly matches the gap between the 2 expansion measurements. The numbers line up in a way that is hard to ignore. The KBC void does not solve every detail of the Hubble tension, but it offers something many other explanations lack. It is based on a real, observed structure, not on imaginary particles or radical new laws of physics. That makes it one of the most down-to-earth explanations currently being discussed. The basic idea can be stated very simply. Inside a region with low density, gravity pulls less strongly. Because of that, the local flow of galaxies looks faster than average. That single fact can subtly shift every distance and speed we measure. In regions with normal amounts of matter, gravity partly counteracts the expansion of space. Inside a sparse region, there is less matter to provide that inward pull. Galaxies feel a weaker tug toward the centre and gain a small extra outward motion on top of the overall expansion of the universe. Astronomers call this extra motion a peculiar velocity. It is not space itself stretching faster. Astronomers call this extra motion a peculiar velocity. It is not space itself stretching faster. It is galaxies moving through space differently because of the uneven distribution of matter around them. Imagine the distribution of matter in the universe as a huge, gentle bowl. The sides of this bowl are built from long cosmic threads and crowded clusters of galaxies, while the inside is strangely empty, missing much of the matter you would normally expect. Because of this uneven layout, gravity does not pull things toward the middle of the bowl. Instead, it tugs outward, toward the heavier walls around the edge. For galaxies trapped inside this hollow, the natural downhill path is not inward, but outward, away from the centre. Now add this steady outward pull to the normal expansion of the universe, the slow stretching of space itself. When astronomers measure how fast galaxies seem to be moving away, this extra push makes the expansion appear faster than it truly is. In other words, our local part of the universe looks like it is expanding more quickly, simply because everything around us is sliding outward from the empty centre of this basin. This effect depends strongly on distance. Near the middle of the hollow, where matter is most scarce, the outward drift is strongest. As you move closer to the edge of the basin, where more galaxies and matter are packed together, this extra motion weakens. Far beyond the boundary, the influence of the hollow fades away entirely, and galaxy motions return to the cosmic average. This gradual change creates a clear and testable prediction. If the idea is correct, measurements made using nearby objects should suggest a slightly faster expansion, while measurements that include more distant objects should slowly drift down toward the true, global value of the universe's expansion. That is exactly what astronomers see. When they measure distances using exploding stars located within a few 100 million light-years, the calculated expansion rate tends to come out a bit higher. As those measurements are extended to include supernovae farther away, the number steps down. The difference is not dramatic, but it is steady and consistent, just what you would expect if we were sitting inside a large, underfilled region of space. The most important part of this explanation is that it does not require any strange new laws of physics. There is no need for unknown forces or exotic particles. Everything follows from ordinary gravity, acting on the mass we can already measure. The only unusual factor is our location. If we lived inside a dense cosmic wall instead of a hollow, we would measure the opposite effect and conclude that the local expansion was slightly slower than average. This leads to a very practical question. How can scientists separate the motion caused by this giant hollow from the true expansion of space itself? And how far out do they need to measure before the influence of our local environment becomes so small that it no longer matters? The answer lies in careful observation. If a massive underfilled region surrounds us, its influence should not be random or chaotic. It should show up as a clear pattern in how the measured expansion rate changes with distance. The logic is simple. The closer galaxies are to the centre of the hollow, the faster they seem to drift away from us. The farther out astronomers look, the weaker that extra motion becomes. This creates what scientists call a distance-dependent Hubble gradient. At distances of a few 100 million light-years, the expansion rate appears slightly higher than the cosmic average. At greater distances, the value slowly declines. At the larger scales, it settles into the same number measured using signals from the early universe. This pattern has already been observed. Surveys of supernovae reveal a small but clear drop in the inferred expansion rate as the volume of space being studied grows. This behaviour matches exactly what would happen if we lived inside a giant basin like the KBC void. It is one of the strongest observational clues that this hollow is not imaginary, but real. This gradient is also extremely useful. By mapping it carefully, astronomers can estimate both how deep the hollow is and how wide it stretches across space, without relying only on galaxy counts. In this way, our cosmic neighbourhood becomes a kind of natural laboratory, where the structure of space reveals itself through the motion of galaxies. However, this test has limits. Beyond a few billion light-years, the signal of the void becomes faint and blends together with other large structures in the universe. To be confident, scientists need many overlapping measurements, not just one technique, but several independent methods that all point to the same conclusion. This is where the oldest light in the universe enters the story. The cosmic microwave background, the faint afterglow left over from the birth of the universe, provides another powerful test. When photons from this ancient radiation travel through regions with different densities, they gain or lose tiny amounts of energy. This process is known as the integrated Sachs-Wolfe effect. In dense regions, gravity can hold photons back slightly, causing them to lose energy as they climb out. In underfilled regions, the opposite happens. The gravitational pull is weaker, so photons leave with a small boost of energy. When astronomers measure these tiny energy changes across the sky, they appear as extremely subtle temperature variations in the background radiation. If the KBC void is real and as large as galaxy surveys suggest, it should leave behind a faint but detectable mark in this ancient light. Its size and position line up with exactly the kind of weak signal that modern, sensitive instruments are capable of finding. Several studies have already reported such hints. No single measurement is strong enough to prove the case on its own, but taken together, the pattern fits well with the presence of a large nearby underfilled region. This means the void is not only visible in galaxy counts and unusual galaxy motions, but is also suggested by the oldest light we can observe. That overlap is crucial. It connects a structure in our local universe to observations on the largest possible scales, linking modern galaxy surveys with radiation left over from the very beginning of time. The real power of the integrated Sachs-Wolfe effect is not that it reveals one specific hollow, but that it shows how local structures interact with ancient light. By combining signals from many regions across the sky, astronomers can detect the faint fingerprints left behind when microwave background photons pass through areas of low density. When researchers applied this method to the region around our own galaxy, they found a weak but consistent signal. The temperature shift was tiny, only a few millionths of a degree, yet it matched the predicted position and size of the KBC void almost perfectly. This is exactly what an underfilled region of this scale should do to passing light. While this signal alone does not prove the existence of the void, it offers strong independent support. It cannot be explained away as dust or instrument errors, because it appears in multiple datasets collected by different instruments. The fact that a structure mapped using nearby galaxies also leaves an imprint on the cosmic microwave background makes the case far stronger. It shows that this hollow is not a trick of observation or survey design. It is a real part of the cosmic landscape, large enough to pull on galaxies, influence redshift measurements, and gently nudge the oldest light in the universe as it passes through our cosmic home. The next step is to look at a very different kind of evidence, one that does not rely on counting galaxies or measuring how bright they appear. Instead, it focuses on how galaxies actually move through space. Astronomers call this shared motion bulk flow, and it describes the way large groups of galaxies drift together across enormous distances, almost like leaves being carried by a slow, invisible current. In a universe that is perfectly smooth and evenly filled with matter, these motions should cancel out when you look far enough. Random movements in one direction would be balanced by movements in another, leaving no clear overall drift. But that is not what astronomers observe. When they measure galaxy motions on very large scales, they find something surprising. Whole collections of galaxies are moving together in the same direction, sliding toward regions of space that contain more matter. Our own galaxy is part of this motion. The group of galaxies that includes the Milky Way is travelling at about 600,000 miles per hour, compared to the faint afterglow of the Big Bang, known as the cosmic microwave background. This speed cannot be explained by the general expansion of the universe alone. Something else is influencing our motion. That influence comes from gravity. We live inside a vast, underfilled region of space, a kind of cosmic hollow. Because there is less matter around us than average, gravity inside this region is weaker. The hollow effectively pushes matter outward. At the same time, far beyond the edges of this empty region lie massive clusters of galaxies and long filaments of matter. Their strong gravity pulls everything toward them. The result is a combined effect. We are being gently pushed out of the hollow, while also being tugged toward heavier structures outside it. When astronomers map these galaxy motions in detail, a clear pattern emerges. Near the centre of the hollow, galaxies tend to drift outward in a smooth, coordinated way. Farther out, beyond the edges of the hollow, galaxy motions point inward toward enormous concentrations of matter in the distance. This pattern fits extremely well with the idea that we are living inside a large region of unusually low density, surrounded by heavier structures on all sides. It explains both our own motion and the gradual changes in velocity that astronomers measure in other galaxy systems. The presence of such a strong and organised bulk flow is one of the clearest signs that this hollow is real. It connects the idea of an underdense region directly to the actual movement of matter in space, not just to how light travels or how bright galaxies look. Because galaxy speeds respond directly to gravity, they reveal where mass truly lies. This makes velocity measurements one of the most powerful tools for understanding the depth and shape of the hollow we inhabit. Astronomers do not rely on galaxy motions alone. By combining measurements of how fast galaxies are moving with surveys that record how their light is stretched by cosmic expansion, they can rebuild a three-dimensional map of the mass around us. This method reveals structures that cannot be seen directly, including regions where matter is missing rather than piled up. When this technique is applied to our own cosmic neighbourhood, the result is striking. It shows a wide, low-density basin surrounding us, enclosed by walls made of galaxy filaments and dense clusters. This structure is not a perfect sphere, but it is fairly balanced in all directions. Its centre lies very close to the position of our local group of galaxies. Its outer edges extend to almost 1 billion light-years away. Along those edges, the number of galaxies increases sharply, marking the transition from the quiet interior of the hollow to the crowded regions where massive filaments link into even larger cosmic structures. Inside the basin, galaxy motions are smooth and orderly, flowing gently outward. Along the walls, those motions change, and galaxies begin to converge toward powerful attractors far beyond the hollow. This behaviour is exactly what theory predicts for a large, gravitationally calm region surrounded by much denser matter. What makes this kind of mapping especially convincing is that it does not depend on a single type of observation. It uses motion itself to reveal the gravitational landscape, and that landscape tells the same story as galaxy counts and measurements of the cosmic microwave background. All of these independent clues point to the same conclusion: we live inside a vast cosmic hollow. The strong agreement between these different methods is why the KBC void has become one of the most intensely studied nearby structures in cosmology. But this discovery leads to a deeper and more troubling question. How can such an enormous and deep hollow exist in a universe that is supposed to be statistically uniform? In a statistically uniform universe, our location should be ordinary, not special in any meaningful way. Yet the KBC void is anything but ordinary. According to standard cosmological models, the chance of finding a basin this large and this empty, so close to our position, is less than 1 in 1,000. That tiny probability is what transforms the void from a curious local feature into a serious cosmological puzzle. Voids of this size are expected to exist somewhere in the universe, but they should be extremely rare and scattered randomly. The odds of not only being near one but actually living deep inside it are even smaller. It is like living exactly at the bottom of a valley in a landscape that is otherwise mostly flat. Where you stand in that valley affects how the surrounding terrain looks, and in the same way, our position inside this hollow affects how we measure the universe around us. Some scientists argue that unlikely does not mean impossible. In a universe containing billions of observable regions, even very rare events are bound to occur somewhere. But if our location really is statistically unusual, then researchers must consider whether that uniqueness is influencing their measurements. This is why the KBC void lies at the heart of debates about the cosmological principle. The cosmological principle states that the universe looks the same in every direction and from every location when viewed on sufficiently large scales. It is the foundation of nearly all the equations used to describe cosmic expansion. If we live inside a rare and massive underdensity, then this assumption may not hold perfectly at our position. Most tests of this principle assume that local irregularities fade away beyond a few 100 million light-years, but the KBC void extends much farther than that, pushing the limits of what can safely be ignored as a local effect. If the principle fails locally, the consequences spread outward. Measurements of distance, interpretations of redshift, and the values of key cosmic numbers could all be affected. This does not mean the universe stops being uniform on the larger scales. It means our local environment may not represent that average condition. Several researchers see the KBC void as a real-world test of the cosmological principle. If many independent observations, including galaxy surveys, exploding stars, the microwave background and galaxy motions all point to the same structure, then it shows that local deviations can be stronger than expected. The debate is not about whether the cosmological principle is true overall, it is about whether it applies cleanly where we happen to live. And that possibility makes our cosmic address far more important than cosmologists once believed. The standard picture of the universe is built on a comforting idea. It assumes that when you zoom out far enough, all the bumps, gaps, and clumps in space begin to smooth out. On scales larger than a few 100 million light-years, the universe is supposed to look roughly the same in every direction. This assumption is what allows scientists to use clean, simple equations to describe the entire cosmos. But the KBC void pushes this idea right to its breaking point. A structure that stretches close to 1 billion light-years across is not something that easily fades into the background. It is simply too large to be ignored. If our home sits inside such a vast region where matter is missing, then our position may actually matter more than cosmologists once believed. Some of the most important numbers we use to describe the universe might not be purely universal after all. The value that describes how fast the universe is expanding, the measured contrast between dense and empty regions, and even estimates of dark energy, could be slightly tilted by where we happen to be standing. This does not mean the models of cosmology are wrong or useless. It means they may need to be more careful about where measurements are taken. The universe may look a little different depending on your cosmic address. Computer simulations strongly support this idea. When researchers create virtual universes that include giant voids, similar in size to the KBC void, they see a clear pattern. Observers placed inside these empty regions almost always measure a faster local expansion and slightly altered values for other key parameters. Observers outside the voids, living in denser regions, tend to measure numbers that line up much more closely with the true cosmic average. This contrast reveals an important but often overlooked truth. The cosmological principle, the idea that the universe is the same everywhere on large scales, is not a law carved into nature. It is a practical approximation. And like all approximations, it works well only up to a point. The KBC void may be the structure that shows us exactly where that point lies. Acknowledging this limit does not break cosmology. Instead, it sharpens it. It offers a possible explanation for why some of our most precise measurements stubbornly refuse to agree with one another. The universe may not be contradicting itself. We may simply be viewing it from an unusual place. Most cosmic voids are far less dramatic. The majority span only tends to a few 100 million light-years. These smaller empty regions are common features of the cosmic web, formed naturally, as gravity pulls matter into long filaments and dense clusters. They are well understood, widely studied, and found everywhere astronomers look. The KBC void, however, belongs to a completely different category. Its radius stretches close to 1 billion light-years, placing it among the largest structures ever identified. Structures of this size are rare, and their influence is enormous. They can shape the motion of galaxies far beyond their visible boundaries, subtly bending measurements of the expansion rate and leaving faint fingerprints on the background radiation left over from the early universe. Astronomers classify voids by both their size and by how empty they are compared to the cosmic average. Small voids produce only mild effects, barely nudging galaxy motions. Medium-sized voids can generate noticeable flows, but their influence remains local. Giant voids like the KBC are different. They are powerful enough to challenge how cosmological ideas are applied in real observations. Because of this, mapping voids of many different sizes has become an important way to test the standard model of cosmology. If enormous, underdense regions like the KBC void turn out to be more common than expected, it could suggest that the early universe produced stronger fluctuations than current theories allow. If they remain as rare as predicted, then our location may simply be unlikely but not impossible. Either outcome is scientifically valuable. The extreme size of the KBC void places it at the far edge of cosmic structure, turning it into a natural laboratory for testing how well our equations survive under unusual conditions. The sheer size of the KBC void is more than an interesting detail. It is the reason its effects are so hard to ignore. A small void might gently push galaxy speeds in one direction. A giant void affects many different measurements at once. When something stretches nearly 1 billion light-years across, its influence spreads over enormous distances. Large voids reshape the flow of galaxies well beyond their edges. They distort distances measured using redshift, bias estimates of the expansion rate, and leave subtle marks on the cosmic microwave background. Their gravitational pull is weak at any single point, but it accumulates steadily over vast regions of space. What makes this especially compelling is how consistent the evidence is. Galaxy counts, unusual galaxy motions, large-scale flows, and background radiation measurements all point in the same direction. We appear to live inside a large underdense basin. Any one of these signals could be brushed off as random noise. Taken together, they form a clear and coherent picture of our cosmic neighbourhood. This scale also makes the KBC void a powerful testing ground for precision cosmology. If theoretical models can explain all of these observations at once, they are likely capturing reality very well. If they cannot, then something important may be missing from our understanding. The KBC void is not just another gap in the cosmic web. It is a stress test for the assumptions that hold modern cosmology together. Every cosmic void can be described using two basic numbers: its size and how empty it is. The size tells us how far it stretches through space, while the density contrast tells us how much matter is missing compared to the cosmic average. For the KBC void, both numbers sit at extreme values. Its radius is close to 1 billion light-years, and its density is roughly 20% lower than average. This combination is crucial because it determines how strongly the void interacts with everything around it. A shallow, empty region would barely influence galaxy motion. A deep and wide one changes velocities across hundreds of millions of light-years, producing smooth, coordinated flows and measurable shifts in redshift-based distances. The boundary between the emptier interior and the denser outer regions acts like a gentle gravitational slope. Galaxies near the centre feel the weakest pull and drift outward more quickly. Galaxies closer to the edge slow down as they approach denser filaments and clusters. This gradual change is what creates the distinct motion patterns astronomers have carefully mapped. These traits make the KBC void a clear example of how cosmic emptiness shapes its surroundings. It is not just an empty region. It is an active structure that quietly rearranges the movement of galaxies and even the path of light itself. Understanding its shape and behaviour is essential for understanding how it can subtly warp our view of the universe as a whole. The outer edge of the KBC void is not like hitting a hard wall or an abrupt boundary. Instead, it is more like a long, gentle slope where the amount of matter slowly increases the farther you go. This gradual change creates a soft but constant pull of gravity that never suddenly stops. Galaxies near the very centre of this vast hollow feel the weakest gravitational tug of all, so they drift outward more quickly and more freely. As these galaxies move closer to the outer regions of the void, the surrounding matter becomes thicker, gravity grows stronger, and their outward motion begins to slow down. This entire structure behaves much like a wide bowl surrounded by raised ridges. Material sitting at the deepest part of the bowl naturally flows outward, while matter closer to the sides feels more resistant and moves more slowly. Over billions of years, this difference in motion slowly reshapes the void. What may have started as a very gentle and blurry underdense region becomes sharper and more clearly defined. The boundary looks stronger not because it was born that way, but because gravity has been quietly sculpting it over immense stretches of time. This sloping structure does more than move galaxies. It also changes how light travels through space. When light particles, called photons, pass through the centre of the void, they move through a region where gravity is weaker. As a result, they gain a tiny amount of energy, like a subtle push forward. When those same photons pass near the edges of the void, they encounter stronger gravity, which slightly bends their paths and changes their energy in the opposite direction. These effects are extremely small, but modern instruments are sensitive enough to measure them. The combination of the gravitational slope and the outward flow of matter explains why the void leaves such a clear and organised signature in the data. The patterns astronomers see are not random or accidental. They are exactly what gravity predicts when matter spreads out inside a massive underdense region. By carefully mapping these smooth gradients, scientists can learn far more than just how big the void is. They can reconstruct its entire story, tracing how a tiny early imbalance grew over time into a structure that now stretches nearly 1 billion light-years across. Light travelling through the KBC void does not behave the same way as light moving through an average part of the universe. As photons cross the emptier interior, they experience weaker gravitational forces and receive a slight boost in energy. When they leave the void and enter denser regions filled with galaxies and clusters, that boost is partially reversed. Each individual change is tiny, but over cosmic distances the effects accumulate. This is why the edge of a void is not just a line drawn on a map. It is a wide transition zone where light can gain or lose energy, depending on the exact path it takes. This process contributes to what scientists call the integrated Sachs-Wolfe effect, which has been detected in the faint background glow left over from the early universe. It also plays a role in the subtle distortions seen in the redshifts of distant galaxies. In principle, two identical galaxies located at the same true distance from us could appear slightly different if one is seen through the void and the other through a denser region of space. The difference is far too small to notice in a single galaxy, but when astronomers measure thousands or even millions of galaxies together, the pattern becomes clear. This is one reason cosmic voids have become powerful tools in modern cosmology. They do not merely rearrange matter, they shape the light that carries the universe's history to our telescopes. When astronomers measure how fast the universe is expanding, they rely heavily on redshift. But redshift is influenced by more than just cosmic expansion itself. Local structures, like enormous voids, also leave their fingerprints on the signal. Inside the KBC void, galaxies gain a small extra outward speed on top of the general expansion of space. This added motion shifts their observed redshifts, making them appear slightly farther away than they truly are. For individual galaxies, this effect is subtle, but when analysed across large surveys, it becomes significant. Detailed sky maps can clearly distinguish galaxies that sit inside the underdense region from those outside it. This is why the KBC void cannot be ignored when scientists calibrate local distance measurements. The effect is especially important for supernova studies. Type Ia supernovae are used as standard candles to measure cosmic expansion, because they shine with nearly the same brightness every time. If a large underdense region adds extra outward motion to the galaxies hosting these explosions, the calculated expansion rate appears higher than the true global value. This explanation fits neatly with the long-standing difference between measurements of the expansion rate taken nearby and those inferred from the early universe. Importantly, fixing this discrepancy does not require exotic new physics or radical changes to our theories. It simply requires recognizing where we are located within the cosmic landscape. Understanding how redshift distortions work is essential if we want to turn raw observations into an accurate picture of the universe. The redshift distortions caused by the KBC void point to a deeper issue known as local bias. If our measurements are made from an unusual environment, they may not accurately represent the universe as a whole. This is one of the strongest reasons cosmologists argue that the void must be taken into account when interpreting data. Imagine using a thermometer placed near a heat source. The thermometer still works perfectly, but its readings are biased by its surroundings. In the same way, our measured expansion rate may be slightly inflated simply because we're sitting inside a low-density region. This bias affects several crucial measurements, including the Hubble constant, galaxy distances, and even estimates of the age of the universe. All of these depend on the assumption that our cosmic neighbourhood is typical. If that assumption turns out to be false, the entire calibration of our cosmic measuring stick shifts. The encouraging news is that local bias can be measured and corrected by combining multiple independent observations. By comparing supernova data, galaxy motion patterns, and background radiation, scientists can determine how much of the discrepancy comes from our location rather than from unknown physics. Acknowledging this bias does not weaken cosmology, it strengthens it, ensuring that our conclusions reflect the universe as a whole, not just the vast hollow we happen to call home. Every extremely accurate measurement in modern cosmology depends on one quiet but crucial step: calibration. No matter which tool astronomers use, whether they study exploding stars that act like cosmic measuring sticks or the faint glow left behind by the early universe, everything rests on carefully connecting what we observe, such as redshift, to how far away something truly is. Redshift tells us how much light has been stretched as the universe expands, but turning that stretch into a reliable distance requires assumptions about the space we live in. If that calibration is influenced by nearby cosmic structures, especially something as enormous as the KBC void, then the results can slowly drift. Not because the universe itself is behaving strangely, but because our viewpoint inside it is unusual. This is why the local cosmic environment cannot be ignored. If astronomers fail to account for it, they may slightly overestimate how fast the universe is expanding or misjudge the true speeds at which galaxies are moving away from us. Even tiny biases at relatively small cosmic distances can spread upward through calculations, quietly influencing the inferred amount of dark energy or the estimated age of the universe. What begins as a small local effect can ripple outward and reshape our understanding of the cosmos on the larger scales. The reassuring part is that distortions caused by cosmic voids are not mysterious or exotic. They follow ordinary gravitational physics. There are no unknown forces hiding inside them. Because of that, their influence can be predicted, modelled and mathematically removed, but only if the structure of the void itself is mapped with great care. This is where the KBC void stops being a curiosity and becomes something far more valuable. It turns into a calibration reference point. By learning its shape, size and gravitational influence, astronomers can fine-tune their measurements and bring nearby observations into better alignment with those made across the wider universe. Improving this calibration may not only soften the long-standing disagreement over the expansion rate of the universe, known as the Hubble tension, but could also uncover subtle patterns that were previously hidden in the data. Our position in the universe is not a minor detail. It actively shapes how we see everything. If we lived in a more typical region, many cosmological measurements might line up more neatly. But residing inside a vast region of low density like the KBC void means that every number we pull from the sky is coloured by context. This is not a mistake or a flaw. It is simply the natural outcome of gravity and cosmic expansion working together. Modern cosmology operates at a level of precision that leaves very little room for error. Tiny differences in measured redshift, brightness, or velocity can shift conclusions about the universe's age, its composition, and even its ultimate fate. If local structures like large voids are ignored, they can quietly introduce systematic offsets. These small shifts also affect how scientists interpret disagreements between different measurements. What might initially look like evidence for new and exotic physics could, at least in part, be the result of our location inside an unusual cosmic neighbourhood. Recognizing that difference is essential. It tells us when we are seeing the universe as it truly is, and when we are simply observing it from a peculiar vantage point. The KBC void serves as a powerful reminder that location matters. It transforms the universe from a simple static backdrop into a dynamic landscape that subtly bends both matter and perception. The void does not rewrite the laws of physics. Instead, it gently bends their observable outcomes, shifting measurements just enough to matter in an era where cosmology is balanced on razor-thin margins of precision. A slight outward motion here, a small redshift bias there, none of these effects are dramatic on their own, but they accumulate. When combined, they can imitate or conceal signals that might otherwise be blamed on entirely new physics. This is why the KBC void has become such an important focus in modern research. It offers a grounded explanation for several puzzles, including part of the tension surrounding the universe's expansion rate, without requiring hypothetical particles or unknown forces. Everything involved is based on well-understood gravitational behaviour. The key factor is scale. A structure nearly 1 billion light-years across has a vast reach. It subtly reshapes the motion of nearby galaxies, affects how light travels, and biases the way cosmic distances are calibrated, all without breaking a single physical law. That is what makes the KBC void so important. It is not a crisis for cosmology, it is a correction. It reminds us that where we observe matters just as much as the equations we use. At today's level of precision, even modest local structures can influence final results. The KBC void perfectly illustrates how environment and measurement intertwine. If its presence were ignored, small biases might be mistaken for signs of new forces or particles. Once the underdensity is properly included, some of those tensions ease. The data does not change, but the interpretation does. As instruments become sharper and surveys more detailed, this interplay between local environment and cosmic inference grows increasingly important. Future observations will measure redshifts and distances with unprecedented accuracy. At that level, even a gentle underdensity can no longer be dismissed as background noise. The void turns raw precision into meaningful context. It reminds us that every observation is made from somewhere, and that somewhere leaves fingerprints on the numbers we trust. At the frontier of precision cosmology, small effects dominate. A fraction of a percent difference in expansion, a slight shift in redshift, or a tiny change in the energy of background light can cascade through calculations and reshape the inferred history of the universe. The KBC void is almost perfectly positioned to produce exactly this kind of subtle influence. A large region of low density does not act like a single, overpowering force. Instead, it introduces gentle, consistent biases across many measurements, including galaxy speeds, brightness-based distances, large-scale flows, and even tiny temperature variations in the cosmic microwave background. None of these shifts are overwhelming on their own, but together they form a coherent pattern that changes how data is interpreted. This is why scientists study the void so carefully. If these effects are ignored, they can amplify or hide signals that seem to point toward new physics. If they are modeled correctly, they sharpen our understanding of the universe without adding unnecessary complexity. The KBC void shows that cosmic structures do not need to be violent or spectacular to matter. Quiet distortions spread across billions of light years can speak just as clearly as explosive events. Cosmic voids are more than empty spaces. Their low-density interiors create calm environments, where subtle physical effects can be observed with far less interference from crowded regions, filled with clusters and filaments. The KBC void, because of its immense size, acts as one of the best natural laboratories for studying how gravity, expansion, and light interact. Inside this vast basin, the gravitational landscape is smoother, making it easier to detect outward motions, redshift gradients, and faint temperature shifts in background radiation. Signals that would be lost in noisier regions stand out here with surprising clarity. The absence of massive structures also reduces uncertainty, turning the void into a clean testing ground for cosmological models. Researchers use this quiet environment to push their theories to the limit. If standard models can reproduce what is observed inside the KBC void, from galaxy motions to distortions in background light, their reliability is strengthened. If not, the discrepancies reveal exactly where refinements are needed. The calm nature of the void is what gives it power. It turns emptiness into precision, offering a place where the universe quietly reveals how it truly works. The KBC void is not just a theoretical concept. This enormous region of low density leaves measurable fingerprints across many independent datasets, and those fingerprints agree with one another. The signals are faint, but they repeat from one method to the next, reinforcing the message that even in its emptiest regions, the universe is still shaping what we see. This is exactly the kind of clear and repeating pattern that immediately catches the attention of cosmologists. When completely different tools are used to study the universe, yet they all begin to tell the same story, scientists know something important is happening. The speeds at which galaxies are moving, the carefully measured distances to exploding stars known as supernovas, and even the tiny temperature differences frozen into the ancient microwave background radiation all line up remarkably well. Each of these measurements comes from a different method, relies on different physics, and is affected by different sources of error. And yet, when they are placed side by side, they point toward one shared conclusion. This kind of agreement is rare in cosmology, and when it appears, it signals that the universe is revealing a deeper truth that can no longer be ignored. The idea that the universe contains enormous regions of near emptiness can feel strange at first, especially when most images of space show glowing galaxies, shining stars, and colourful clouds of gas. Yet when scientists began to map the universe on its largest scales, they discovered that matter is not spread evenly at all. Instead, it gathers into long threads and thick knots, leaving behind vast open regions called cosmic voids. These voids are not small gaps. They can stretch across distances so large that light would need hundreds of millions of years to cross them. Understanding how such immense emptiness came to exist has become one of the most fascinating puzzles in modern cosmology, because it touches on gravity, the earliest moments of the universe, and the slow process by which galaxies were born and grew. To begin thinking about void formation, it helps to imagine the universe shortly after it began. In its earlier stages, matter and energy filled space almost evenly, like a fog spread across an endless landscape. However, this fog was not perfectly smooth. Tiny differences existed from place to place. In some regions, matter was just a little bit denser than average, while in others it was slightly thinner. These differences were incredibly small, far smaller than anything humans can directly see, but they mattered deeply. Over time, gravity took these small differences and slowly amplified them, turning gentle ripples into the vast structures seen today. Gravity plays a central role in the story of voids because it is the force that pulls matter together. Where matter starts out slightly denser, gravity becomes stronger, pulling in even more material from nearby space. These regions grow heavier and richer, eventually forming galaxies, groups of galaxies, and enormous clusters. On the other hand, where matter begins slightly less dense, gravity has less to work with. Matter there is more easily pulled away toward neighbouring dense regions. As this happens, these underfilled areas lose more and more material, becoming emptier over time. What begins as a mild shortage slowly turns into a cosmic desert. One way to picture this process is to imagine a large table covered with a thin layer of sand. If you gently shake the table, grains of sand will slide together into small piles, leaving bare patches behind. The piles represent dense regions where matter gathers, while the bare patches resemble cosmic voids. The shaking is not violent, and the sand does not disappear. It simply moves. In a similar way, matter in the universe flows slowly under the influence of gravity, leaving behind regions where very little remains. Another key idea connected to void formation comes from the concept of cosmic inflation. Inflation refers to a brief period very early in the universe's history, when space itself expanded at an incredibly rapid rate. During this time, tiny quantum fluctuations were stretched to enormous sizes. These fluctuations became the seeds of all later structure. Inflation did not create voids directly in the form we see today, but it set the initial pattern of tiny differences in density that gravity later shaped. Without inflation, the universe might have been far smoother, leaving gravity with little to work on and producing a very different cosmic landscape. Inflation also helps explain why voids can be so large. Because space expanded so quickly, small variations were blown up to scales far larger than galaxies, or even clusters of galaxies. When inflation ended and the universe settled into a slower expansion, these variations remained frozen into space. Over billions of years, gravity enhanced them. Regions that began slightly emptier than average had a long head start, allowing them to grow into the immense voids observed today. As time passed and the universe cooled, matter began to clump together more effectively. Dark matter, an invisible form of matter that does not emit or absorb light, played an especially important role. Dark matter makes up most of the matter in the universe, and its gravity acts as a hidden framework guiding the motion of normal matter. Where dark matter gathered, gas followed, eventually forming stars and galaxies. Where dark matter was sparse, little else could take hold. Many scientists believe that cosmic voids are regions where dark matter itself is thinly spread, making it difficult for galaxies to form and survive. Galaxy formation is therefore deeply tied to the existence of voids. Galaxies are not born everywhere. They require certain conditions, including enough matter and gravity to pull gas together until it becomes dense and hot enough for stars to ignite. In voids, these conditions are rare. Gas is more spread out, gravity is weaker, and interactions between galaxies are infrequent. As a result, voids tend to contain very few galaxies, and those that do exist there are often small, faint, and isolated. Over time, the contrast between dense regions and voids becomes stronger. Galaxies in crowded areas merge, grow larger, and become part of massive clusters. Meanwhile, voids continue to lose matter as gravity pulls it toward the edges. This creates a kind of cosmic flow, where material streams out of voids and into surrounding filaments and clusters. These flows further empty the voids, reinforcing their emptiness and sharpening their boundaries. Some theories suggest that voids do more than simply form as a byproduct of structure growth. They may actively influence the behaviour of the universe on large scales. Because voids contain less matter, the expansion of space inside them may proceed slightly faster than in denser regions. This difference could subtly affect measurements of cosmic expansion, adding another layer of mystery to their role in the universe. Another way scientists think about void formation involves the idea of hierarchical growth. In this view, small voids form first, then merge over time to create larger ones. Early in the universe, many small underdense regions existed. As matter flowed away from them, neighbouring voids expanded and eventually joined together, forming giant empty regions. This merging process mirrors the way small galaxies combine to form larger ones, but in reverse, with emptiness instead of matter. The shape of voids also offers clues about their origin. They are not perfect spheres. Instead, they tend to be irregular, stretched by the gravitational pull of surrounding structures. Their boundaries are often defined by filaments of galaxies, creating a sponge-like pattern across the universe. This pattern, sometimes called the cosmic web, shows how voids, filaments, and clusters are all part of a single connected system shaped by gravity and expansion. Computer simulations have become a powerful tool for studying void formation. By starting with conditions similar to those thought to exist shortly after the universe began, scientists can let gravity and expansion play out inside a virtual universe. These simulations produce networks of filaments and voids that closely resemble what telescopes observe. By adjusting factors such as the amount of dark matter or the properties of inflation, researchers can see how voids change, offering insights into which theories best match reality. One interesting aspect of voids is that they are not completely empty. Even the largest voids contain some matter, including dark matter, thin gas, and occasional galaxies. These galaxies often have unusual properties. Because they live in isolation, they experience fewer interactions with neighbours. This can make them simpler in structure and slower to evolve, almost like time capsules preserving earlier stages of galaxy development. The mystery of void formation also touches on deeper questions about the balance of forces in the universe. Gravity works to pull matter together, while cosmic expansion works to push space apart. Voids can be seen as regions where expansion has gained the upper hand, allowing space to stretch faster than matter can fill it. This delicate balance between attraction and expansion shapes the universe on its grandest scales. Some scientists explore whether alternative theories of gravity could change how voids form. If gravity behaves differently over vast distances than current models suggest, voids might grow larger or emptier than expected. Studying voids could therefore offer a way to test fundamental laws of physics in environments very different from dense regions like galaxies or clusters. Another layer of interest comes from how voids affect light travelling through them. Light passing through a void experiences less gravitational bending than light passing near dense clusters. Over great distances, these effects can subtly alter the appearance of distant galaxies and the background glow of the universe. By studying these changes, scientists hope to learn more about the distribution of matter and the true nature of emptiness itself. The role of inflation, gravity, and galaxy formation in creating voids shows how interconnected cosmic processes are. Inflation sets the initial pattern, gravity sculpts it over time, and galaxy formation marks where matter succeeds in gathering. Voids emerge naturally from this interplay, not as anomalies, but as essential features of the universe's structure. As observations improve, astronomers continue to map voids in greater detail, measuring their sizes, shapes, and contents. Each new map reveals the same striking pattern of emptiness surrounded by structure, reinforcing the idea that voids are a fundamental part of the cosmos. They are not simply gaps between galaxies, but vast regions that tell a story about the universe's earliest moments and its long evolution. Thinking about void formation invites a shift in perspective. Instead of focusing only on where matter is, it asks us to consider where matter is not, and why. These empty regions hold clues about invisible forces, ancient events, and the slow dance of matter across cosmic time. By studying voids, scientists are learning that emptiness itself can be a powerful guide to understanding how the universe came to look the way it does. In this way, the mystery of void formation becomes a story of contrasts. Small differences grow into vast separations. Gentle forces acting over immense spans of time carve out regions of near nothingness. Gravity, inflation, and galaxy formation work together, shaping not only what fills the universe, but also what is left behind. On a more philosophical level, the existence of vast cosmic voids challenges human intuition. Emptiness on such scales is hard to imagine. A void can be so large that even if every star in our galaxy were removed, the remaining emptiness would still be tiny compared to the emptiness of a cosmic void. These regions remind us that the universe is not designed to suit human expectations. It follows simple physical laws, applied over immense scales and immense times, producing structures that are both beautiful and strange. The mystery of void formation is not a mystery because it lacks explanations, but because it reveals how much can arise from simple beginnings. Tiny variations, stretched by inflation and shaped by gravity, grow into a universe where emptiness and structure coexist in a delicate balance. Voids are not failures of formation, not gaps where something went wrong. They are the natural outcome of a universe governed by gravity, expanding space, and the slow, patient dance of matter over billions of years. As scientists continue to study voids, they refine their understanding of how the universe evolved from a nearly uniform state to the richly structured cosmos seen today. Each void tells a story about its surroundings, about the flow of matter, and about the fundamental forces at work. By listening to these stories, cosmologists deepen their understanding of the universe as a whole, finding meaning not only in the bright clusters of galaxies, but also in the vast, silent spaces between them. We live inside a vast region of space that contains much less matter than average, like a huge shallow bowl scooped out of the universe, and this emptiness quietly nudges the local expansion of space to move a little faster than usual. The first clues come from extremely detailed maps of the cosmos. Astronomers carefully record where galaxies are located and how fast they are moving toward or away from us along our line of sight. They then subtract the smooth overall expansion of the universe, known as the Hubble flow, to expose the leftover motions, called peculiar velocities. When these motions are drawn on a map, something striking appears. The arrows showing galaxy movement tend to point outward from our region, as if everything nearby is gently sliding away from a central low point. The strongest outward drift is seen closer to the interior of this basin, while the motion becomes weaker as you move toward its edges. When these velocity maps are compared with distance measurements from exploding stars called supernovae, the same story shows up again. Galaxies closer to us suggest a faster rate of expansion, while measurements that cover much larger stretches of space settle back toward the universal average value. Another layer of evidence comes from the oldest light in existence, the faint microwave glow left over from the birth of the universe. As these ancient photons travel through our underfilled region, they pass through weaker gravitational fields than they would in denser areas. Because gravity slows light slightly, passing through a gravitationally shallow region lets these photons leave with just a bit more energy. When scientists stack and combine many patches of the sky, they detect a very subtle increase in temperature that lines up with both the direction and the rough size of this empty region. No single patch of sky proves the case on its own, but when all of them are combined, the signal behaves exactly the way theory predicts for a wide and deep cosmic hollow. The most compelling part is how well all these independent lines of evidence agree with one another. Each method has its own sources of uncertainty and potential bias, yet they all paint the same picture: galaxies flowing outward, expansion that depends on distance, and a faint fingerprint left on the background radiation. When very different techniques arrive at the same conclusion, the odds of pure coincidence shrink dramatically, and the argument for a real physical structure grows much stronger. This is not a speculative adjustment made to rescue a theory. It is a measured feature of our cosmic environment, one that helps define how we should interpret everything else we observe in the universe. At first glance, cosmic voids may seem like nothing at all, but that apparent emptiness is exactly what makes them so powerful for science. In regions where matter is scarce, gravity is weak, clutter along the line of sight is reduced, and many messy astrophysical effects fade into the background. A broad, underdense basin provides astronomers with a clean stage on which to watch how cosmic expansion behaves without too many distractions. In such simple environments, tiny signals that would normally be drowned out inside crowded clusters of galaxies can rise above the noise. Inside this hollow, the change in density is smooth and predictable, which allows scientists to measure the collective outward motion of galaxies and compare it directly with what standard gravity predicts. If expansion appears slightly faster near the centre and gradually relaxes toward the boundary, that smooth gradient can be mapped to estimate how deep and how large the structure truly is. This same region is also ideal for testing observations based on light. Photons crossing a shallow gravitational landscape leave behind a minuscule temperature step, which becomes detectable only when many observations are combined. These voids also enable crucial cross-checks using different techniques. Weak gravitational lensing, which normally stretches and magnifies galaxy shapes, turns into a gentle anti-lensing effect here, subtly diluting those shapes instead. Distortions in redshift space stretch galaxy distributions along the line of sight, revealing the hidden velocity field beneath. Even the acoustic scale used as a cosmic measuring stick can be compared inside and outside the basin to search for slight offsets. The real strength of this approach lies in its method. Each probe has its own weaknesses, but when all of them point in the same direction, confidence steadily increases. If theoretical models match the observations, the void sharpens our measurements. If they do not, the disagreement highlights exactly where our assumptions may fail. In a universe filled with brilliant galaxies, massive clusters, and sprawling filaments, empty regions might seem unimportant. Yet for cosmologists, these quiet zones can be just as revealing as the brightest structures. A wide underdense basin like the one surrounding us offers a rare, calm view of how cosmic expansion behaves where gravity is weakest. In these hollows, the underlying physics becomes clearer, and that clarity is what gives them such scientific value. This particular local structure is so large and so deep that its imprint appears across many independent sets of data, including outward galaxy flows, distortions in redshift measurements, and faint temperature changes in the background sky. Each signal on its own is subtle, but together they outline a feature that is extremely hard to dismiss as mere chance. It is not a single measurement that reveals the shape of this basin, but the convergence of many. By treating this region as meaningful information rather than as a source of error, astronomers can refine how they measure the expansion of the universe. Low-density environments act like natural laboratories, where gravitational effects are less tangled and faint. Signals stand out more clearly. Far from being irrelevant, emptiness sharpens our view of the cosmos and reminds us that the spaces between galaxies can teach us just as much as the galaxies themselves. When observations are made from inside a low-density basin, the first challenge is separating local influences from universal truths. The most direct way to do this is to compare measurements that are sensitive to nearby structure with those that average over enormous volumes of space. If they disagree at short distances but agree when larger regions are considered, that difference points to the influence of our local environment rather than to new exotic physics. Nearby indicators form the first rung of this process. Standard candles such as certain types of supernovae, the tip of the red giant branch, and water masses anchor the local distance ladder. These methods are highly sensitive to peculiar velocities and to the slightly faster expansion inside the hollow. To look farther out, cosmologists rely on baryon acoustic oscillations and the acoustic scale in the cosmic microwave background, which span such immense distances that local irregularities are washed away. If the nearby measurements suggest a higher expansion rate than these global rulers, the gap reflects location, not mistake. The same logic applies to galaxy motions. Maps of galaxy flows within a few 100 million light-years show a clear outward trend. As these maps are extended toward the edges of the region and beyond, the drift weakens and begins to align with more distant gravitational influences. When redshift data and distance measurements are combined, they reveal a step-down pattern exactly as expected from an underdense environment. Additional cross-checks strengthen the conclusion. Weak lensing shows a small deficit in convergence, redshift space distortions reveal stretching along the line of sight, and background radiation displays a subtle temperature step. When all of these independent signals line up, local bias can be cleanly removed, leaving the global expansion rate intact. One of the longest-standing puzzles in cosmology is the difference between the expansion rate measured nearby and the value inferred from the early universe. A large underdense region like the one we inhabit can explain part of that difference, without introducing any new forces or unknown particles. It is not about exotic physics. It is about where we are. Inside a cosmic hollow, weaker gravity allows galaxies to drift outward a little faster, and light travelling through this region experiences less slowing, making nearby objects appear slightly farther away than they would in denser parts of the universe. When astronomers take all of these observations and use them to build what is known as the cosmic distance ladder, an interesting pattern appears. Nearby measurements point to a slightly larger value for the Hubble constant, meaning space around us seems to be expanding a bit faster than expected. But when scientists look much farther out into the universe, where the influence of our local surroundings fades away, the measured expansion rate slowly settles back toward the global average. This shift does not require a dramatic push. Even a very gentle outward motion is enough to change the numbers by a few percent, and at today's level of precision, a few percent is a very big deal. Careful studies show that this local effect alone can ease some of the tension between measurements made nearby and those drawn from the early universe. It does not magically solve the entire puzzle, but it changes how we think about it. The difference is not only hidden in the data itself, part of it comes from our position in the vast cosmic web and the environment we happen to live in. The physical reason behind this local boost in expansion is surprisingly simple. In crowded regions of the universe, gravity is strong. It slows galaxies down and pulls them inward toward dense clusters. In regions where matter is sparse, the opposite happens. Gravity is weaker, and galaxies are not held back as much. They are free to drift outward just a little faster than the average cosmic expansion. That small extra push is exactly what shows up in measurements made close to home. Picture two identical galaxies placed at the same true distance from us. One lies along a line of sight that passes through this large, empty hollow, while the other sits along a direction filled with denser cosmic structures. The galaxy inside the low-density region will appear to be moving away slightly faster. That tiny difference is enough to quietly bias the distance ladder if it is not properly accounted for. As astronomers look farther and farther out, this local influence gradually weakens. Once the line of sight reaches the surrounding filaments and clusters, the gentle outward drift gives way to the stronger gravitational pull of massive structures. At that point, the measured expansion rate settles closer to the true global value of the universe. This explains why nearby observations consistently give slightly higher numbers than measurements tied to very distant rulers. Because we are positioned deep inside this broad cosmic basin, the outward drift is strong enough to matter for precision cosmology. It is not loud or dramatic, but it is real, measurable, and important. Ignoring it would subtly stretch or shrink the scale of the universe itself. This outward drift caused by our surrounding hollow is not just a theoretical idea. Astronomers can detect it directly. They track the motions of galaxies by measuring their redshifts, and then compare those motions to the smooth, idealized Hubble flow. The difference between the two reveals a coherent pattern of motion that matches the shape of the underdense region around us. The effect is strongest near the interior, where gravity is weakest and galaxies show the largest departures from what would otherwise be expected. As you move outward, the signal softens, and beyond the edge of the basin, it is overtaken by the gravitational pull of filaments and clusters. This gradual change lines up almost perfectly with maps of large-scale structure built from redshift surveys and velocity reconstructions. These findings do not rest on a single experiment or a lone dataset. They come from many independent surveys that together track thousands of galaxies spread across hundreds of millions of light years. What gives this signal real weight is the agreement between these separate measurements. A pattern seen once could be dismissed as chance. A pattern that appears again and again across survey after survey becomes a physical reality. This is why local underdense regions matter so much. They may be invisible to the naked eye and quiet in their influence, but their fingerprints are clearly written into the motions of galaxies drifting through them. In precision cosmology, even a small bias can shift the entire picture. Measurements of the Hubble constant now aim for accuracy at the level of only a few percent. A local boost caused by our cosmic hollow fits squarely within that range. It is small enough to be overlooked at first glance, yet large enough to reshape the numbers scientists depend on. A mild outward drift nudges the inferred expansion rate upward. A faint gravitational gradient subtly alters redshift distributions. A tiny change in the energy of background photons leaves its mark in temperature maps of the cosmic microwave background. None of these effects dominates the data on its own, but together they gently push key cosmological parameters away from their true values. This is why local structure sits at the centre of the debate over the so-called Hubble tension. If part of the disagreement comes from the environment we live in, then the amount of new, exotic physics needed to explain what remains is smaller. The mystery does not vanish, but it becomes sharper and more focused. In a field where fractions of a percent truly matter, ignoring these quiet biases is not an option. They may be subtle, but their influence reaches across the entire framework of modern cosmology. To really understand why the environment matters, it helps to look closely at how this bias forms. When light from nearby galaxies reaches us, its redshift carries two messages at once. One reflects the smooth, overall expansion of the universe. The other comes from local motions shaped by the gravitational landscape of a low-density region. That second contribution adds a gentle outward drift to the measured velocity. If this effect is not included in the models, distance calculations become distorted. Galaxies appear slightly farther away than they truly are, and the inferred expansion rate rises. The observations themselves are not wrong. The interpretation is simply incomplete. Recognizing and modelling this extra component turns what looks like a deep cosmic mystery into a measurable correction. This bias does not stop with redshifts alone. It also influences how bright supernovae appear, how peculiar galaxy velocities are reconstructed, and even the subtle temperature patterns seen in the cosmic microwave background. Each line of evidence leans in the same direction. The real strength of the effect comes not from its size in any single dataset, but from its consistency across many different kinds of observations. Because the source of the bias is physical, well-defined and rooted in gravity, it can be measured, modelled and corrected for. In doing so, it transforms from a hidden complication into a powerful tool, one that helps make our picture of the universe clearer and more precise than ever before. When astronomers try to measure how fast the universe is expanding, they do not simply look at redshifts and read off an answer. Redshifts are only the starting point. Those raw measurements are carefully processed, modelled and corrected to remove effects that come from our immediate cosmic neighbourhood. One of the most important corrections is accounting for the influence of nearby large-scale structures, especially the low-density region we live in. Because our region of space contains less matter than average, galaxies around us experience a gentle outward drift. This extra motion slightly adds to the expansion signal we observe. Astronomers treat this effect the same way they treat instrument errors or random measurement uncertainty. It is measured, modelled, and then subtracted out. Large surveys such as Cosmic Flows 3 map how galaxies move across hundreds of millions of light years. These maps reveal organised large-scale motions pointing outward from our region, exactly what you would expect if we were inside a vast cosmic hollow. This measured pattern of motion, known as the velocity field, is then used to correct distance measurements. These include well-known cosmic yardsticks such as Type 1a supernovae and stars at the tip of the red giant branch. The correction is small, only a few percent, but at today's level of precision, that small adjustment is enough to noticeably change the final results. The same idea also applies to distances inferred directly from redshift. By removing the extra outward boost caused by our local environment, astronomers find that the locally measured expansion rate moves closer to the value inferred from observations of the early universe. The long-standing tension between these numbers shrinks, not because of strange new physics, but because we have properly accounted for where we are located in space. Our position in the universe is not a minor detail that can be ignored. It is a measurable factor that must be included. Once measured, it becomes part of the calibration process that sharpens our understanding of the cosmos. For many years, local structures were treated as annoyances that should be averaged away. Modern precision has changed that view. Astronomers now use these structures as valuable sources of information. The low-density region around us is not background noise. It is a real, measurable feature that can improve cosmological models when handled correctly. A clear example comes from the Sloan Digital Sky Survey. By mapping millions of galaxies and combining those maps with velocity reconstructions from Cosmic Flows 3, researchers uncovered a large, coherent outward flow extending across hundreds of millions of light years. Instead of ignoring this signal, cosmologists now build it directly into their models. This allows local measurements of the Hubble constant to be corrected in real time. The flow becomes a calibration anchor rather than a disturbance. As a result, the gap between local and global expansion rates narrows, and the structure we live in becomes part of the measuring stick itself. This change in perspective is subtle but powerful. Precision cosmology is not about pretending we observe the universe from nowhere. It is about clearly recognizing where we are and using that knowledge to our advantage. The region around us is not an isolated bubble of emptiness. It is part of the cosmic web, a vast network of filaments, walls, and voids that defines the universe on its larger scales. These low-density regions fill nearly 80% of the universe's volume, while most matter is packed into thin filaments and dense clusters. The underdense region we inhabit is simply one piece of this enormous structure. This pattern arises naturally in the standard cosmological model, as matter collapses into clusters and sheets. The spaces between them gradually empty out, forming huge basins with weak gravitational pull. The hollow surrounding us is especially large, stretching close to 1 billion light-years across, large enough to leave clear fingerprints on measurements of local expansion. Its position within the cosmic web explains the observed motion of galaxies, a weak gravitational pull near the centre, stronger influence near the edges, and a smooth transition to the gravitational tug of nearby filaments. Beyond those edges lie massive attractors that guide the flow of matter. By placing our measurements within this larger network, cosmologists can separate the effects of our environment from the overall behaviour of the universe. We're not observing the cosmos from a neutral location. We are measuring it from a structured, evolving node within the cosmic web. The low-density basin around us is closely connected to larger structures. Its boundaries link to long filaments that stretch for hundreds of millions of light-years, channeling matter toward distant regions such as the Great Attractor and the Shapley Supercluster. These connections explain why the local outward drift fits naturally into the universe's grand flow. Inside the hollow, gravity is weak, allowing galaxies to drift outward relative to us. Near the boundary, distant clusters begin to dominate, bending galaxy paths along filaments. The result is a smooth change from outward motion inside the hollow to inward motion beyond it, exactly what simulations of void filament networks predict. Observations confirm this picture, velocity reconstructions from cosmic flows. 3 show organised streams moving from the interior of the basin toward major attractors in the surrounding web. The match between these measured flows and known structures is far too precise to be a coincidence. It is the gravitational fingerprint of connectivity on the larger scales. By tracing these large cosmic currents, astronomers can place our local underdensity in its proper context. It is not an isolated void, but one part of a vast interconnected network of motion that shapes the universe. To understand our place in this web, astronomers do more than count galaxies. They carefully track how those galaxies move. Every redshift contains 2 signals mixed together: the smooth expansion of space itself and the additional motion caused by gravity from nearby structures. By combining redshift data with independent distance measurements, researchers can separate these effects and reconstruct the velocity field around us. Surveys like Cosmic Flows 3 apply this method to thousands of galaxies spread across hundreds of millions of light-years. The resulting maps clearly show outward motion near the centre of the basin, weakening toward the edge and bending along filaments toward distant attractors. This is not just a theoretical idea. It is a direct measurement built from real observations. Multiple distance indicators are used together, including Type 1a supernova, tip of the red giant branch stars, surface brightness fluctuations, and water masers. Each method has its own uncertainties, but when combined, they reveal a consistent flow pattern that no single technique could uncover alone. These velocity maps turn the idea of a local underdensity into something tangible. The motion of galaxies themselves becomes the evidence. The flow is the structure, and through it, astronomers can see how our cosmic neighbourhood shapes what we measure when we look out at the expanding universe. One of the most subtle yet powerful clues that confirms the presence of a large empty region around us comes from something known as the integrated Sachs-Wolfe effect. This effect is incredibly delicate, but it carries enormous meaning. It involves the oldest light in the universe, the cosmic microwave background, which has been travelling through space since the universe was still very young. As these ancient photons move across the cosmos, they pass through regions where gravity is stronger or weaker. Each time they do, they gain or lose a tiny amount of energy, almost like a whisper of information left behind by the structure of space itself. When light passes through a wide, shallow region with very little matter, like the basin surrounding our location in the universe, something special happens. Because this region has weaker gravity than average, photons do not lose as much energy climbing in and out of it. At the same time, the universe is expanding while the photons are inside this region. That expansion slightly stretches the gravitational landscape, allowing the photons to leave with a tiny net gain of energy. This extra energy shows up as an extremely faint warm spot in the cosmic microwave background sky. The effect is extraordinarily small. The temperature change is only a few microkelvin, which is far below what any single observation could clearly detect. On its own, one patch of sky looks no different from random noise. However, astronomers have found a clever way to reveal this hidden signal. They use a method called stacking, where many regions of the sky that align with the same large structure are combined and averaged together. When this is done, random fluctuations cancel each other out, and the real signal slowly rises above the noise. When scientists applied this technique to the region surrounding us, they found a weak but consistent temperature increase in the same direction, and at roughly the same scale as the underdense region mapped by galaxy surveys. This match is striking. The shape and size of the temperature pattern in the ancient background light line up closely with the geometry derived from modern maps of galaxy positions. That agreement strongly supports the idea that this hollow is real and not just a mistake in the data. What makes this evidence especially compelling is its independence. Unlike galaxy counts, redshift measurements, or velocity maps, the integrated Sachs-Wolfe effect does not rely on local distance estimates or nearby measurements. Instead, it is written directly into the oldest light in the universe. This light left its source long before galaxies like ours even formed, and yet it still carries a record of how space has changed along its journey. When both the motion of galaxies and this ancient radiation point to the same structure, the chance that it is a coincidence becomes extremely small. This convergence of evidence is what turns the idea of a local cosmic hollow from a simple hypothesis into a measurable feature of the universe. Velocity maps show galaxies drifting outward. Redshift surveys trace the large-scale distribution of matter, and the integrated Sachs-Wolfe effect reveals the same structure imprinted on the cosmic microwave background. Each signal on its own is faint and easy to dismiss. Together, they form a clear and consistent picture. Detecting this effect requires patience and precision. No single observation is strong enough to stand on its own. Instead, astronomers combine dozens or even hundreds of aligned sky regions. Each individual temperature change is only a few microkelvin, far below the noise level of a single measurement. But when many such regions are averaged together, the noise fades away, and the true signal remains. This same method has already been used successfully to study enormous empty regions known as supervoids elsewhere in the universe. The result near our location shows the same subtle warming that theory predicts. This approach is powerful because it provides a clean and independent check on other measurements. It does not depend on how fast galaxies appear to move, how distances are calibrated, or how red shifts are interpreted. The signal is embedded directly in the background radiation itself. That makes it one of the most reliable cross-checks available in modern cosmology. This is how cosmology works at its best. Progress does not come from one dramatic discovery, but from many small clues slowly lining up. A faint outward flow of galaxies, a tiny temperature shift in ancient light, and a subtle distortion in redshifts may seem insignificant on their own. But when they all point in the same direction and match the same scale, they form a pattern that is impossible to ignore. This careful stacking of evidence does more than confirm the existence of the structure around us. It also helps refine our understanding of the universe as a whole. By recognizing and correcting for the effects of our local environment, astronomers can bring local measurements of the universe's expansion rate closer to the value inferred from the early universe. The result is less tension between different measurements, smaller uncertainties, and a clearer cosmic picture. The strength of the case for our local underdensity does not come from any single signal. It comes from the harmony between many weak but independent probes. Like quiet voices joining together into a chorus, These signals speak clearly about the structure of the universe we inhabit and our place within it. In cosmology, what truly matters is not how much data you have, but how well different kinds of evidence agree with each other. A very faint signal that shows up independently in 3 separate sets of observations is far more convincing than a loud signal that appears in only one place. When scientists look at how galaxies are moving, they see a gentle outward flow, as if everything around us is slowly drifting away from the centre of a broad, shallow basin in space. Surveys that measure redshift, which tell us how fast galaxies are receding, reveal a matching region where matter is unusually sparse. At the same time, temperature patterns in the ancient light of the universe, known as the cosmic microwave background, carry a subtle imprint called the integrated Sachs-Wolfe effect, and that imprint lines up with both the motion of galaxies and the low-density map. What makes this especially powerful is that none of these methods depend on the same tools, the same assumptions, or even the same kinds of measurements. One uses galaxy motions, another relies on distances and redshifts, and another examines tiny temperature changes in relic radiation from the early universe. When all of them point to the same picture, their agreement becomes a strong sign that the structure we are seeing is real. This layered strategy is how astronomers learn to trust extremely delicate results. It is the same logic that led to the acceptance of dark energy and the discovery that the universe's expansion is speeding up. No single piece of evidence is convincing on its own, but together they form a compelling story. Our local cosmic environment, which was once treated as an annoying complication that had to be corrected away, has now become a kind of natural testing ground where many lines of evidence meet. Because so many independent observations intersect here, the picture of our cosmic neighbourhood becomes sharper and much harder to dismiss. One of the most important outcomes of carefully mapping this nearby region of low density is its effect on what is known as the Hubble tension. This tension refers to the stubborn mismatch between the expansion rate measured in the nearby universe and the rate inferred from the early universe. It has grown into one of the central puzzles of modern cosmology. However, not all of this disagreement necessarily points to unknown physics. Part of it may simply come from the fact that we are making our measurements from inside a slightly unusual part of the cosmic web. The outward flow of galaxies in our region gently boosts the value of the expansion rate we measure locally, known as the Hubble constant. When scientists carefully model this environmental effect and subtract it, the inferred value shifts downward. This brings it closer to the expansion rate derived from the cosmic microwave background. The discrepancy does not vanish completely, but it shrinks to a level that is more in line with what could reasonably arise from statistical scatter and systematic uncertainty. The strength of this explanation lies in its simplicity. It does not demand new particles, strange forms of energy, or a collapse of the standard lambda cold dark matter model. It only asks us to recognize and account for the measurable influence of the cosmic neighborhood we happen to live in. If some portion of the tension comes from our location rather than from the deep laws of nature, then cosmologists can concentrate more effectively on what remains. They can sharpen their tools to distinguish between what the universe truly is and where we happen to be positioned within it. Every measurement in cosmology is shaped by perspective. We cannot step outside the universe to observe it from a neutral vantage point. We are always observing from the inside. Because of that, local structures will inevitably leave their fingerprints on the data we collect. The real challenge is learning how to separate what belongs to our immediate environment from what reflects the fundamental rules that govern all of space and time. If our region of the universe is less dense than average, then the expansion rate we measure nearby will naturally appear a bit higher. This effect is not an illusion or a mistake. It is a straightforward and expected consequence of general relativity. Once this bias is corrected, local observations line up more closely with the global picture of the universe. Any remaining difference after that point must arise from deeper physical causes, not from cosmic geography. This distinction is crucial. Without it, we risk mistaking a local quirk for a universal truth. With it, the data become cleaner, and cosmological models can be tested with much greater precision. The universe itself does not need to change to explain the numbers we measure. Sometimes the key is simply understanding where we are standing within it. Perspective may sound like a limitation, but in practice it becomes a powerful calibration tool. By carefully accounting for our local surroundings, we we turn our own cosmic neighbourhood into a reference frame that helps us better understand the universe as a whole. The Hubble tension has become one of the loudest and most talked about arguments in modern cosmology. Many scientists describe it as a possible warning sign that something new and unexpected may be missing from our understanding of the universe. But before anyone rewrites the laws of nature or introduces exotic new particles, researchers first turn their attention inward, toward the local environment in which these measurements are made. Not every disagreement in science means something strange is happening. Some differences appear simply because of where we are standing and how we are looking. Our region of the universe sits inside a large area with less matter than average. This underdense neighbourhood gently pushes galaxies outward, creating a slow, subtle flow away from the centre. That extra outward motion adds a small boost to how fast the universe appears to be expanding when measured nearby. As a result, the locally calculated expansion rate, known as the Hubble constant, ends up slightly higher than it would be in a perfectly average region of space. When scientists carefully model this effect and correct for it, the disagreement with measurements from the early universe does not disappear completely, but it becomes noticeably smaller and easier to handle. This tells us something important. Part of what once looked like a deep cosmic mystery may simply reflect cosmic geography rather than new forces or unknown forms of matter. This way of thinking is not special to this one problem. In precision cosmology, researchers always check for systematic effects first. They examine everything from how telescopes are calibrated to how local motions of galaxies are modelled before jumping to bold conclusions. The universe often hides complexity in plain sight, and careful analysis is the only way to uncover it. By separating the influence of our environment from signals that might be truly fundamental, cosmologists are not ignoring the Hubble tension. Instead, they are sharpening it. After correcting for our location in the cosmic web, a smaller but stubborn gap remains between the Hubble constant measured nearby and the value inferred from the cosmic microwave background. This leftover difference is now the main focus of attention. It is cleaner and more honest because the confusing effects of local geography have been stripped away. Several explanations for this remaining gap are still being considered. It could come from unaccounted, systematic errors, such as tiny issues with instrument calibration, survey design, or the methods used to measure cosmic distances. It might even be a rare statistical fluctuation, unlikely but not impossible. Or it could point to something deeper, such as a process in the early universe that changed how fast space expanded long before the first galaxies formed. The key point is that whatever remains after environmental corrections must either be hiding in the data or rooted in fundamental physics itself. This clarity is what makes correcting for environmental effects so powerful. The story of the Hubble tension does not end here, but it can now be told with sharper outlines and fewer distractions. Once local influences are accounted for, the remaining discrepancy truly demands an explanation. If the structure around us does not fully explain the problem, then the answer may indeed lie in new physics. Several ideas have emerged, each carrying major implications for the history of the universe. One leading proposal is early dark energy. In this picture, the universe experienced a brief surge of extra energy density during the first few 100,000 years after the Big Bang. This temporary boost would have sped up expansion slightly at early times, changing the conditions at recombination and raising the early universe estimate of the Hubble constant. While this can bring the two measurements closer together, it requires extremely precise timing and strength to avoid conflicting with other well-tested observations. Another possibility involves changes to gravity itself. If gravity's strength evolved subtly over cosmic time, the expansion history of the universe would shift without introducing a new energy component. These models are mathematically elegant, but they face strong limits from observations of large-scale structure. A third idea focuses on neutrinos. If neutrinos have different masses or interactions than assumed in the standard model, they could slightly alter the expansion rate during both early and later periods of cosmic history. None of these ideas has been proven, and none fully solves the tension on its own, but each makes clear predictions that can be tested. This is where cosmology moves from simply measuring numbers to truly understanding the universe. Before embracing exotic explanations, cosmologists always check the ground beneath their feet. Environmental effects, instrument behaviour, and data selection biases are the first suspects in any high-precision measurement. This careful discipline is why the Hubble tension is treated not as a single mystery with one dramatic solution, but as a layered problem that must be peeled back step by step. The underdense region around us is the clearest example of this approach. Its presence can be measured, its influence on expansion can be predicted, and its effect can be corrected using well-established methods. This stands in contrast to ideas like early dark energy or modified gravity, which require changes to the theoretical framework of cosmology itself. In science, the simplest explanations that match the data are always tested first. This does not reject the possibility of new physics. Instead, it provides a roadmap. By carefully measuring and removing environmental contributions, any remaining discrepancy becomes cleaner and easier to interpret. A puzzle that once looked messy and confusing turns into a precise target. In this sense, our position in the cosmic web is not a problem to overcome, but a starting point. It marks the place where the search for deeper answers begins. Correcting for the local environment does more than clarify the Hubble tension. It improves the overall precision of cosmology. By removing known biases, astronomers can measure fundamental properties of the universe with greater confidence. The clearer our local picture becomes, the sharper our global understanding grows. This approach is especially important in the era of extremely precise surveys. Missions such as the Euclid mission, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed to measure cosmic expansion, track the growth of structure, and study dark energy with unmatched accuracy. For instruments like these, a local bias of 2 or 3% is not a small detail. It is a systematic effect large enough to blur entire conclusions if left uncorrected. By treating the cosmic basin around us as a calibration factor rather than a nuisance, future surveys can align local and global measurements more smoothly. This means smaller uncertainties, fewer ambiguities, and stronger tests of any proposed new physics. The lesson is simple but profound. Understanding where we are is part of understanding the universe itself. The clearer our view of our cosmic home, the better we can read the deeper story written across space and time. The next generation of experiments will make environmental effects impossible to ignore. These observatories will map billions of galaxies, trace how structure grows across cosmic history, and pin down the nature of dark energy with extraordinary precision. That precision cuts both ways. Even the smallest local bias will stand out clearly. The underdense region around us, once seen as a curiosity, will become a crucial calibration anchor. Velocity fields, redshift patterns, and background temperature maps will be modelled together instead of separately. The environment will no longer sit quietly in the background. It will be built directly into the measurement process itself. Rather than subtracting local effects after the analysis is finished, future surveys will include them from the very beginning. This integrated approach promises better consistency between nearby and distant measurements, and a clearer answer to whether the remaining Hubble tension reflects real new physics. In a very real sense, the most advanced telescopes ever built will also be the most aware of where they stand in the universe. For many decades, astronomers and cosmologists treated the structure of our local cosmic neighbourhood as nothing more than a nuisance, a source of noise that needed to be removed from the pristine equations describing the universe. It was something to ignore, a complication that interfered with the clean view of cosmic expansion. But now, that perspective is changing completely. Instead of being seen as an obstacle, the vast underdensity surrounding us, the enormous region where matter is less concentrated than average, is becoming a powerful tool, a fixed reference point that future surveys can use to sharpen and refine their measurements. This shift reflects a broader transformation in the field of cosmology itself. In the early days of cosmological experiments, the uncertainties in measurements were so large that local irregularities could safely be overlooked. Scientists could afford to ignore them because the errors were already substantial. Today, however, modern instruments and telescopes can measure cosmic phenomena with precision down to fractions of a percent. At this level, even the tiniest systematic effect can no longer be dismissed. A cosmic structure stretching almost 1 billion light-years is not a trivial rounding error. It is a real feature that must be included in the data. By integrating multiple sources of information, such as the motions of galaxies, the distribution of redshifts, and the faint signals left in the cosmic microwave background, Astronomers can now analyse the universe in a fully interconnected way. When the local environment is treated as part of the model itself, cosmological parameters can be determined more accurately, with fewer ambiguities and tighter confidence ranges. What was once regarded as a bothersome nuisance is now emerging as a kind of calibration standard. Understanding exactly where we are in the universe is becoming just as crucial as understanding what we observe. Future cosmological surveys will not merely correct for local bias after the fact, they will be designed around it. Mission planners already take into account the gravitational landscape near our position in the universe to predict how it will influence incoming data for major experiments, such as the Euclid mission or the Vera C. Rubin Observatory. Even a small error in this modelling could ripple through the analysis and distort every parameter derived from the data. This approach represents proactive integration. Rather than treating the local underdensity as an external correction, it is incorporated directly into the statistical models and likelihood functions used to infer cosmic parameters. This strategy allows the various elements, galaxy velocity fields, distortions in redshift measurements, and temperature variations in the cosmic microwave background, to be handled together in a consistent framework. The local environment can no longer masquerade as a signal from the distant universe. It is a subtle change, but a profound one. Cosmology is no longer pretending to observe from some abstract nowhere. It is openly acknowledging its vantage point and folding that perspective into the analysis from the start. By embedding local bias into the design of experiments, these missions will not just measure the universe, they will measure it with a full awareness of exactly where we stand. As measurements become more precise, the room for ambiguity shrinks. Once environmental effects are fully modelled and incorporated into the data pipelines, any remaining discrepancies, like the persistent Hubble tension, will become a cleaner probe of the universe itself. This is when hypotheses about exotic physics, such as early dark energy or modifications to gravity, can be tested under the sharpest possible conditions. In the past, noise from our environment blurred the distinctions between competing theories. But when that noise is measured instead of ignored, each hypothesis must stand entirely on its predictive power. If early dark energy exists, its signal will remain even after all local corrections are applied. If it disappears, then the original tension was never evidence of new physics at all. The same logic applies to other ideas, from the ordering of neutrino masses to hypothetical interactions between dark energy and matter. Precision is not simply about producing more exact numbers. It is about drawing clearer lines between genuine physical effects and artifacts caused by our position in space. By refining those boundaries, the next generation of surveys will do far more than collect data. They will actively determine which ideas survive the scrutiny of reality. When cosmologists talk about measuring the universe, they are really measuring the differences between what they observe and the theoretical baseline they rely on. For decades, that baseline quietly assumed that our vantage point did not matter much. But the discovery of a vast underdensity surrounding us has forced a reconsideration. If we live in a hollow, then the baseline itself must be rewritten to reflect that reality. This does not mean that the laws of physics change depending on location. Rather, it means that the way we interpret observations must change. The interplay of galaxy motions, redshift distortions, and temperature patterns in the cosmic background all come together to form a new reference frame tied to our location. Once this frame is included in the analysis, the influence of the local environment becomes an integral part of the standard model of measurement, not an afterthought to be cleaned up later. With this shift, cosmology is moving from treating the local universe as a nuisance to acknowledging it as a measurable, predictable component of the cosmic landscape. Future discoveries will not just come from studying distant galaxies, they will also emerge from understanding the ground beneath our feet. The baseline has always existed. Now we are finally defining it with the precision the universe demands. Even after fully accounting for the underdensity around us, correcting for the local environment does not entirely erase the Hubble tension. A small persistent gap remains between measurements of the early universe and those of the late universe. This is where attention moves from local geography to the fundamental workings of the cosmos itself. Several theories attempt to explain this residual difference, exploring ideas such as new forms of energy, subtle modifications to gravity, or properties of elusive particles like neutrinos. Unlike environmental corrections, these concepts probe the underlying physics that drives the universe's evolution. To test them effectively, cosmologists first need a clean baseline. Once the noise from local structure is removed, any remaining signal is much more likely to point to something genuinely new. The next great adventure in cosmology is not about pinpointing our location in the cosmos, but about uncovering what the universe is truly made of and how it behaves on its largest, most unimaginable scales. One of the leading ideas scientists are exploring to explain the puzzling Hubble tension is called early dark energy. Imagine a mysterious form of energy that existed only briefly, just a fleeting burst in the universe's infancy, which would have momentarily sped up the expansion of space itself. This is very different from the dark energy we know today, which dominates the universe and drives its accelerated expansion. This early surge of energy would have vanished long before galaxies even formed, yet its faint fingerprints could still be hidden in the cosmic microwave background, the afterglow of the Big Bang. If such an energy field flickered into existence for only a few 100,000 years after the universe's birth, it could have subtly shrunk the sound horizon, the cosmic measuring stick imprinted on the microwave background, raising the calculated value of the Hubble constant without upsetting other well-established cosmological measurements. This elegant and intriguing idea has drawn attention because it aligns remarkably well with the data, though it does not come without its challenges. The timing and intensity of this early energy burst must be perfectly tuned. Too much would disturb the formation of cosmic structures, too little would leave the Hubble tension unsolved. Even so, it remains one of the most active and exciting areas of theoretical research. A reminder that sometimes the key to understanding the universe today lies in its very first heartbeat. Another approach to the Hubble tension does not involve adding any new energy at all. Instead, it asks a bold question. Could the very force that drives the universe's expansion, gravity itself, have changed over time? In models of modified gravity, the strength of gravity might have shifted slightly over billions of years, subtly altering how space stretches without adding anything new to the cosmic mix. If gravity were just a little weaker in the early universe, the expansion would have proceeded slightly faster than we currently expect. That would reduce the inferred age of the universe at the time of recombination, the moment when light first escaped the dense plasma of the early cosmos, and it would increase the early universe estimate of the Hubble constant, potentially bringing it closer to the values we measure in our cosmic neighbourhood today. Unlike early dark energy, this idea is about rewriting the rules of how things interact rather than adding entirely new ingredients to the universe. It is theoretically elegant, yet it faces tough observational tests. Even tiny deviations from Einstein's general relativity can ripple through the growth of cosmic structures, the bending of light by gravity, and the patterns we see in the cosmic microwave background. For modified gravity to work, it must reproduce all the remarkable precision of the standard cosmological model, while simultaneously solving the Hubble puzzle. Though it may not be the ultimate answer, it forces cosmologists to confront a profound question. Has gravity itself remained unchanged since the dawn of time? A third path leads us to the most elusive particles in the cosmos, those that can pass through entire planets as if they were ghosts, neutrinos. In the standard cosmological model, neutrinos are nearly massless and play only a subtle role in shaping the early universe. But if they behave differently than we assume, if they are heavier, more interactive, or have hidden properties, they could leave a measurable imprint on the universe's expansion. The key is how neutrinos affect the growth of space in the early cosmos. Heavier or more interactive neutrinos would slow down the early expansion slightly, changing the size of the sound horizon at recombination. A smaller sound horizon would then push the inferred Hubble constant higher, bringing it closer to local measurements. Unlike early dark energy or modified gravity, this idea does not invent a new force or field. It simply tweaks the behavior of a particle we already know exists. That makes it particularly appealing, because its predictions can be tested not only with cosmic observations, but also with experiments here on Earth. If neutrinos are hiding extra mass or secret interactions, they may hold one of the clearest keys to understanding the universe's expansion. Some scientists look even further, beyond known particles and forces, into the enigmatic dark sector itself, the mysterious realm that dominates the universe yet remains largely invisible. If dark matter and dark energy interact, even faintly, their subtle dance could alter the universe's expansion history and help explain the Hubble tension. In these scenarios, dark energy may have been slightly stronger in the early universe, gradually transferring energy to dark matter over time. This would have increased the expansion rate in the past, shrunk the sound horizon, and raised the inferred Hubble constant, bringing it closer to what astronomers measure nearby. This idea is elegant because it does not require inventing an entirely new force, only a gentle coupling between two components that already govern the cosmos. But it is also delicate. The energy exchange must be perfectly balanced, or it would disrupt the formation of galaxies and the bending of light across the cosmos. The dark sector is largely invisible, making it both one of the most flexible and one of the most challenging frontiers in modern cosmology. If the Hubble tension hides here, it will take a new generation of observations to uncover its signature. Among the more speculative possibilities is phantom energy, a strange form of dark energy that grows stronger over time, accelerating the universe's expansion faster than the standard model predicts. In such scenarios, the equation of state of dark energy drops below -1, pushing expansion to intensify with time. This could allow the present-day Hubble constant to be higher without changing the physics of the early universe, potentially easing the tension. But this idea comes with risks. Phantom energy often leads to theoretical instabilities, including scenarios where the universe might end in a catastrophic Big Rip. Despite these dangers, cosmologists continue to study these models because they provide a direct way to influence the universe's late-time expansion. Even a tiny departure from a constant dark energy equation of state can subtly shift the cosmic timeline. Phantom energy may not be the neatest or most likely solution, yet it serves as a reminder that the universe sometimes hides its secrets in the most unexpected corners, challenging us to keep an open mind and explore every possibility. Another idea lies somewhere between the steady, predictable universe described by the standard lambda CDM model and the wild extremes imagined by phantom energy. This idea is called time-varying or running dark energy. In these models, dark energy, the mysterious force pushing the universe to expand, does not stay constant. Instead, its strength changes slowly over cosmic time. Imagine dark energy as a gentle tide that rises and falls rather than a fixed, unchanging sea. If the dark energy was slightly stronger in the more recent past, it could naturally make the measured Hubble constant larger, without creating any wild or catastrophic effects in the future. The real strength of this approach is flexibility. Unlike early dark energy, which is limited to a narrow window right after the Big Bang, running dark energy can influence the universe over billions of years. This means it can be carefully adjusted to fit both the ancient universe seen in the cosmic microwave background and the universe we observe nearby today. The challenge is that this effect is subtle. It hides in the tiny differences between cosmic distances measured at different times, and only the most precise surveys, like the Euclid mission or the Nancy Grace Roman Space Telescope, might detect it. If dark energy evolves slowly, the universe may not actually be accelerating at a constant rate. It could simply be patient, revealing its gradual changes over time. Another subtle way to tweak the early expansion of the universe is by adding extra light particles, sometimes called dark radiation or exotic relativistic species. If there were slightly more of this relativistic energy in the very early universe than the standard model predicts, it would naturally push the Hubble constant measured from the cosmic microwave background closer to the values seen today. The mechanism is straightforward. More radiation means the universe expanded faster in its infancy, which shrinks the sound horizon, the cosmic yardstick imprinted in the early universe. This method is appealing because it doesn't require rewriting gravity or the physics of the universe after recombination. It only changes the initial energy budget. The big question, of course, is what these extra particles might be. They could be sterile neutrinos, particles similar to axions, or something entirely unexpected. Whatever their identity, their influence would ripple through the cosmic microwave background, the formation of the first elements in Big Bang nucleosynthesis, and the structure of galaxies. Future high-precision surveys of both the cosmic microwave background and large-scale cosmic structures may reveal whether this extra radiation is real or simply a theoretical idea waiting to be discarded. Even more complex models imagine splitting dark energy into two parts. One behaves like normal, constant dark energy, while the other evolves with time. These hybrid models aim to combine the stability of the standard lambda CDM universe with the flexibility of early or running dark energy. In these scenarios, one part of dark energy drives the accelerated expansion we see today, while the other influenced the expansion in the early universe. By shaping the universe's growth at two separate times, these models can fit both early and late observations, a feat single-component models struggle to achieve. The trade-off is complexity. Two-part models introduce more parameters, making them harder to test and easier to overfit. They also require careful tuning to avoid conflicting with precise measurements of the cosmic microwave background and galaxy surveys. Despite the challenges, this approach is gaining attention. As observational data becomes sharper, hybrid models could provide a flexible yet testable framework for resolving the Hubble tension without overturning everything else we know about the cosmos. At the moment, cosmology does not have a single, tidy solution. The Hubble tension has become a delicate puzzle with many interconnected pieces. Every hypothesis, from early dark energy to modifications of gravity, from extra neutrinos to hybrid dark energy, explains part of the story, but none can close the gap alone. This is why cosmologists rely on multiple independent lines of evidence: the sound horizon measured from the cosmic microwave background, baryon acoustic oscillations, local distance ladders, and velocity field reconstructions. Each one anchors a different corner of the problem, and when they align, faint signals can become robust conclusions. It is entirely possible that the ultimate solution will not be a single breakthrough. Instead, it may be a layered answer, part local environment, part measurement systematics, and part new physics. This is often how progress in cosmology occurs, not through a single hammer blow, but by steadily tightening the net around the truth. The puzzle remains unsolved, but it is clearer than ever, and in science, clarity is the first true step toward discovery. As the debate over the Hubble tension intensifies, a quiet revolution is unfolding in the way we map the universe. Future observations will do more than refine individual measurements. They will weave together multiple layers of data: galaxy positions, peculiar velocities, gravitational lensing, and the cosmic background radiation. This multi-dimensional mapping marks the dawn of a new era in cosmic cartography. At its heart lies the cosmic web, a vast network of filaments, clusters, and voids that directs the motion of all cosmic structures. High-resolution surveys will allow cosmologists to reconstruct this structure with unprecedented precision, separating the local from the global and the environmental from the fundamental. Our position within this web is no longer incidental, it is part of the story itself. This transformation turns cosmology from simple curve fitting into detailed three-dimensional mapping. By combining the geometry of the cosmic web with precise measurements of expansion, scientists can uncover signals that were once buried in noise. We are moving from rough sketches of the universe to detailed blueprints, and each new layer of data brings us ever closer to understanding how everything fits together. The cosmic web is not just a poetic idea. It is a tangible, immense structure stretching across the universe. Imagine a sprawling network of glowing threads and dense nodes extending for billions of light years with enormous empty spaces in between, like the gaps in a giant celestial tapestry. Galaxies do not float randomly through space. Instead, they move along these filaments, drawn by gravity over billions of years, gathering together in clusters at the intersections where the pull is strongest. For a long time, astronomers could only outline this structure in rough strokes, but recent surveys are revealing it in stunning detail. By combining the results of redshift measurements, weak gravitational lensing, and velocity maps, scientists can reconstruct not just the current locations of matter, but also how it moves and changes over time. This cosmic cartography is more than a beautiful visualization. It exposes the underlying scaffolding that has guided the evolution of the universe. It explains why galaxies cluster where they do, why the universe expands unevenly in different regions, and how local features, like vast underdense areas, fit into the greater cosmic design. Each filament traced and each void mapped brings humanity one step closer to understanding the full architecture of the universe. The cosmic web did not emerge from nothing. It grew from tiny variations in the density of the early universe. Some regions were just a little denser than others, and over billions of years, gravity amplified these small differences, pulling more matter into them and forming filaments and clusters, while the slightly emptier regions expanded faster, forming the vast voids we observe today. This process follows the familiar laws of physics. In the lambda-cold dark matter model, gravity pulls matter together while dark energy stretches space apart. Filaments form the connective tissue between these forces, channeling matter into clusters that act as anchor points. Simulations of this evolution reveal it with breathtaking clarity. A smooth, almost uniform early universe slowly transforms into a foamy, complex structure, where filaments act like highways guiding the flow of galaxies. Our own cosmic neighbourhood, a hollow surrounded by these filaments, is just one small example of this grand pattern. Galaxies are not stationary lanterns scattered randomly in the dark. They drift slowly but persistently along the gravitational currents of the cosmic web. Filaments act like invisible highways, directing matter toward clusters and superclusters, while enormous voids push galaxies outward as they expand. This constant motion gives the universe its large-scale dynamism. Velocity maps reveal these flows with astonishing precision, showing streams of galaxies curving along filaments like rivers across a landscape, converging where gravity is strongest. These motions are not random. They follow the hidden geometry of the web. Even the movement of our own galaxy is shaped by distant gravitational attractors and the expansion of nearby voids. Understanding this flow changes how we interpret cosmic expansion. Galaxies are not simply drifting on an expanding grid, they are surfing the invisible currents of gravity. To measure the universe accurately, astronomers must account for this motion as distinct from the smooth background expansion. Every galaxy participates in a grand cosmic choreography, written not in the light of stars but in the very shape of space and time. Voids might look like empty nothingness, but they are far from passive. As the universe expands, these low-density regions grow faster than their surroundings, pushing matter outward and enhancing the structure of the cosmic web. In many ways, voids act like hidden engines, driving large-scale flows and shaping how galaxies and clusters evolve. Simulations show that voids do not expand evenly like perfect spheres. They grow irregularly, responding to the tug of nearby filaments and clusters. This uneven growth stretches the web, feeding matter into surrounding structures, while deepening the hollow regions themselves. Our own region is just one small example of this ongoing cosmic dance. Voids also serve as powerful tools for understanding the universe. Because they are less disturbed by messy astrophysical processes, their shapes and growth patterns provide clear clues about how gravity and dark energy operate. Studying them offers a complementary window into the universe's geometry, independent of clusters or exploding stars. In short, voids are not empty. They are silent, active players in the cosmic story. The filaments of the cosmic web form what astronomers often call the skeleton of the universe. These long, thin structures contain most of the universe's matter, threading through vast voids and connecting clusters like the joints of a cosmic spine. Mapping this skeleton requires combining many observational techniques. Redshift surveys show where galaxies are distributed on the larger scales. Weak lensing uncovers the hidden scaffolding of dark matter. Velocity reconstructions reveal how galaxies flow along the filaments. When combined, these approaches produce a three-dimensional map of matter across the largest scales ever observed. This skeleton is not just an aesthetic curiosity. It shapes the evolution of the cosmos itself. Filaments funnel matter into clusters, guide the formation of galaxies, and even influence star formation by regulating how gas flows between regions. To understand the universe, one cannot simply examine individual galaxies. One must trace the invisible threads that connect them, the bones of the cosmos. Filaments also shape the lives of galaxies. Streams of matter flowing along these structures feed galaxies with gas, controlling the pace of star formation and the growth of stellar populations over billions of years. A galaxy's location on the web can influence its evolution as much as its mass or size. Galaxies deep inside filaments grow steadily, nourished by a continuous inflow of cold gas. Galaxies near nodes, where filaments intersect, experience more chaotic interactions, often merging with neighbours. Meanwhile, galaxies on the edges of voids evolve more slowly, starved of fresh material. These environmental differences leave lasting fingerprints on galaxy shapes, ages, and chemical compositions. Understanding these effects is essential to interpreting what astronomers observe. Cosmology is not just about the positions of galaxies, it is about how their surroundings shape what they become. In the grand cosmic dance, the filaments of the universe are far from passive threads. They are active highways, tirelessly transporting gas, dark matter, and energy, fueling the growth of galaxies and shaping the vast architecture of the cosmos. Where these filaments meet, colossal intersections called clusters emerge, gravitational giants where thousands of galaxies gather like cities at the crossroads of invisible highways. These dense hubs are the beating hearts of the cosmic web, where matter has been flowing and colliding for billions of years. Clusters are more than just gatherings of galaxies. They are natural laboratories on a scale impossible to recreate on Earth. Their immense mass allows scientists to witness the intricate interplay between gravity, dark matter, and ordinary matter on cosmic scales. Galaxies feed on material streaming along filaments, with gas and dark matter spiraling inward. As they collide and settle into the cluster's gravitational grip, they heat up, forming searing plasma visible in X-rays. Gravitational lensing bends light around these massive structures, revealing hidden mass and showing a dynamic environment where galaxies merge, evolve, and even cannibalize one another. These clusters also act as anchors, holding the shape of the cosmic web itself. Their locations trace the regions where the universe's earliest density fluctuations were the strongest, the ripples left over from the first moments after the Big Bang. By studying how clusters are distributed, cosmologists can test the expansion history of the universe and refine the models that describe its fundamental behavior with astonishing precision. But the story does not end with clusters. Beyond them lie the superclusters, monumental structures spanning hundreds of millions of light years. These are not bound in the traditional sense. Instead, they influence the cosmic landscape through their sheer mass, their gravitational pull, and the flows of galaxies around them. Superclusters act like giant cosmic basins, subtly directing the movement of galaxies and shaping the expansion of the surrounding voids. Structures such as the Shapley supercluster and the Laniakea supercluster illustrate the staggering scale of these formations. Galaxies within them do not merely drift apart with the universe's expansion. They stream along invisible rivers of gravity toward deeper wells, tracing paths shaped billions of years ago. Superclusters are powerful tools for probing the geometry of the universe and the mysterious force we call dark energy. Their patterns reveal how structure grew from the almost uniform early universe, and their flows reflect how space itself stretches over time. They remind us that the cosmos is not random but exquisitely organized, a tapestry of filaments, clusters, superclusters, and voids interwoven by gravity, dark energy, and the primordial ripples from the Big Bang. This cosmic web is alive, stretching and evolving over billions of years. Galaxies flow along filaments, voids expand like slowly inflating bubbles, and the geometry we see today is just a snapshot of a story that began with tiny fluctuations in the early universe. Modern surveys have finally given us the ability to trace these patterns with remarkable detail. By understanding how these structures form and interact, scientists are learning not only the shape of the cosmos but also the physical laws that govern it. The universe is a complex, patterned tapestry, and deciphering its designs is the key to understanding its past, its present, and its possible future. Every structure we observe, voids, filaments, clusters, superclusters, is more than an astronomical curiosity. They are the physical code of the universe, written in matter and space-time, carrying the memory of what happened in the first fractions of a second after the Big Bang. Cosmology is unique among sciences because it cannot repeat its experiments. Instead, it reads a single, vast experiment spread across billions of light years. Each galaxy's motion, every stretched filament, and every hollow void contains clues about the universe's expansion, composition, and the constancy of its fundamental laws. Our place in this vast structure is not a distraction but part of the story. Understanding where we sit sharpens how we interpret every observation, from the cosmic microwave background to measurements of the Hubble constant. The cosmic web is both a map and a message, a record of what the universe was, what it is, and what it may become. We often imagine observing the universe from a distant, impartial vantage point, but in reality, we are embedded within this cosmic web. Our home lies inside a vast underdensity, surrounded by filaments stretching for hundreds of millions of light years. Every measurement we make passes through this local cosmic filter. Far from being a limitation, this is essential context. Just as ancient navigators had to know their position on Earth to cross the seas, modern cosmologists must map their place in the universe to understand the signals they detect. Correcting for our location turns raw observations into deep insight. In this way, cosmology is as much about understanding ourselves and our position in the cosmic web as it is about understanding the universe itself. Perspective in cosmology is everything. Every redshift, every photon of the cosmic microwave background, every measurement of expansion carries a faint signature of where we stand. By acknowledging this perspective, cosmology becomes more than passive observation. It is an act of translation. What we see is not the universe itself, but the universe as it appears from here. By correcting for our vantage point, we draw closer to the true geometry of the cosmos. Understanding local structure is not a footnote, it is the foundation. It ensures that when we speak of the universe's age, shape, and fate, we do so in a language free of local distortions. The universe has not changed the rules of observation. It has shown us how to read them correctly. The universe stretches beyond imagination, a vast expanse that seems impossible to fully grasp. Yet, the journey to understanding it begins not in the farthest reaches of space, but close to home, right in our cosmic backyard. By carefully mapping the neighbourhood around us, the emptier regions, the dense filaments threading through space, and the gentle flows of galaxies along these strands, cosmologists can start to peel away the distortions that have long blurred our view of the cosmos. What was once dismissed as background noise now emerges as a vital clue, a signal that guides us toward the universe's deeper truths. This approach reflects a larger principle in science itself. Clarity begins with knowing exactly where you are. Just as geologists must understand the terrain beneath their feet to interpret the history written in rocks, cosmologists must comprehend the structure beneath their telescopes. Only then can they measure the universe's true expansion, chart the real distribution of matter, and trace the curvature of space and time across cosmic scales. This is not a side path, a detour from the grand questions of cosmology. It is the very foundation upon which answers must be built. Every universal truth begins with local understanding, and as that understanding sharpens, the gap between what we observe and what truly exists begins to close. For centuries, humanity gazed outward, striving to make sense of the stars, planets, and galaxies. Modern cosmology shows that to see the universe as it really is, we must also look inward, to our own position within the cosmic web. Every observation we make is shaped, sometimes subtly and sometimes dramatically, by the gravitational contours of our surroundings. Understanding those contours with precision transforms a blurry view into a crystal clear picture. This change in perspective marks a quiet revolution. Our location in the cosmic web is not an obstacle to be removed. It is an anchor from which everything else can be measured. Once that anchor is precisely known, the vast panorama of the universe snaps into focus. Expansion rates, flows of galaxies, and measurements of cosmic structure stop contradicting each other and begin to form a coherent whole. The power of knowing our position is immense. It turns perspective into precision. It allows cosmologists to move from arguing over conflicting numbers to uncovering genuine physical truths about the universe itself. Where we are is not a trivial detail. It is the key to seeing everything else with clarity. Cosmology is a science of subtle signals. A shift of even a fraction of a percent in the Hubble constant can ignite debates that last for years. A tiny irregularity in the cosmic microwave background can reshape the way we model the entire universe. In this field, context is everything. By carefully accounting for the gravitational influence of empty regions, filaments, and flows, small discrepancies that once seemed mysterious are revealed to be artifacts of our location, rather than signs of exotic new physics. This clearing of the stage allows genuine discoveries to shine. Today, the most ambitious cosmological surveys integrate environmental modelling directly into their analyses. Local structures are no longer treated as noise to ignore. They are embraced as crucial signals. Context becomes a lens, and through that lens, the universe comes into sharper focus. Precision begins not among the distant stars, but right here, where we stand. For much of its history, cosmology imagined humanity as a detached observer. floating outside the universe and peering in. Modern science has overturned that notion. We are not distant spectators. We are participants, measuring the universe from a specific singular point in its vast network of structures. The story we tell about the cosmos must begin with where we actually are. This realization does not shrink cosmology. It sharpens it. It replaces vague assumptions with meticulous modelling, turning what was once discarded as background noise into a powerful tool for understanding. Our local environment is no longer an error to be swept aside. It is an integral part of the equation. With this grounded perspective, cosmology regains what it lost for decades: context, and with context comes comprehension. The universe ceases to be a cold abstraction of numbers and formulas. It becomes a coherent, living system of matter, energy, and structure, with us embedded within it. This is the quiet revolution happening behind the headlines. Not merely better measurements, but a deeper, more accurate way of reading the cosmic story. Perspective might sound like a soft philosophical concept, but in cosmology, it has profound consequences. A small miscalculation of our location ripples through measurements of distances, velocities, and expansion rates. The very debate over the Hubble constant demonstrates how crucial such details can be. When our environment is ignored, the universe appears inconsistent. When it's properly accounted for, the pieces begin to fit together seamlessly. Perspective is no longer a footnote, it is a core element of science. Our local underdensities, the surrounding filaments, and the flows on the larger scales are not mere scenery. They shape the numbers we use to describe the cosmos. The lesson is simple yet powerful. Where you stand determines what you see. This is true for telescopes and humans alike. By anchoring our models to our actual place in the cosmic web, cosmology becomes not only more precise, but also more honest. Perspective does not distort the universe. Perspective reveals it. The Hubble tension is often spoken of as a problem, a challenge that needs to be fixed. But perhaps it is better to think of it as a rare opportunity, a clue handed to us by the universe itself. Every mismatch between measurements taken from the early universe and those from the later universe is like a tiny signal, whispering secrets about either the way we observe our cosmic surroundings or the way the universe truly behaves. What once appeared to be an obstacle, something that blurred our vision of the cosmos, has now become a kind of lens, revealing truths hidden beneath the surface. By carefully studying our local cosmic environment, the cosmic neighborhood we inhabit, the sparse voids nearby, the filaments of galaxies threading through space, and the flows of matter, cosmologists have begun to sharpen their tools. The uncertainty that once muddied our measurements of the universe's expansion is slowly being transformed into a source of clarity. Each new refinement strips away another layer of confusion, gradually exposing the pure geometry of space and time itself. This, at its heart, is the essence of scientific progress, turning ambiguity into precision, not by ignoring complexity, but by understanding it, embracing it, and learning to read it. The local cosmic environment is not an enemy to truth. On the contrary, it is a key part of how truth is uncovered. The journey to a clear understanding of the cosmos does not begin in the farthest galaxies, billions of light years away. It begins here, in our own cosmic backyard. Long ago, humanity believed that we were at the center of everything. Modern cosmology shattered that illusion. We are not the center of the universe, but our position still matters. It shapes what we see, how we measure it, and the stories we tell about the cosmos. This is not a return to the old idea of geocentrism. Instead, it is the recognition that every observer in the universe exists within their own cosmic frame. No one observes from a perfectly neutral vantage point. Acknowledging that frame is what allows observation to become true measurement. This is how the Hubble constant, once a puzzle of contradictions, begins to reveal the underlying reality. By seeing ourselves not as detached outsiders but as situated observers, cosmology gains both power and precision. We stop pretending to look from nowhere and start measuring from somewhere, and that somewhere is vital. The universe may have no center, but our center, our vantage point, is real, and it is essential to understanding everything else. In most sciences, experiments can be repeated from many different locations. In cosmology, however, there is only one experiment: the universe itself, and we observe it from exactly one point in space and time. That means the observer is inseparable from the measurement. Every photon we detect, every redshift we record, every rate of expansion we infer carries the subtle imprint of our cosmic location. Modern cosmology increasingly treats the observer as part of the system, not as a passive bystander. Our position in space is not an inconvenience to be corrected, it is a variable to include. By folding our cosmic environment into the equations, what once looked like contradictory results begins to align into a coherent, understandable picture. This approach does not make science less objective, it makes it more honest. By admitting where we stand in the universe, we approach the underlying reality rather than a distorted shadow of it. In cosmology, the observer is not outside the experiment, we are in the middle of it. Numbers alone do not create knowledge, they must be placed in context, interpreted through the lens of where we are, in order to form true understanding. For decades, cosmology gathered extraordinary measurements, the glow of the cosmic microwave background, the redshifts of distant galaxies, the expansion rates of the universe. But too often, these numbers were treated as if they were gathered from nowhere. Today, the field is learning to place those numbers back in the universe from which they came, in a universe that is structured, interconnected, and observed from a very specific point. The Hubble tension is not just a statistical mismatch, it is a map of how perspective, cosmic structure, and fundamental physics intersect. By interpreting it through the lens of our environment, cosmologists are transforming confusion into a sharper, clearer vision of reality. The discipline returns to its roots. Cosmology has always been about reading a single universe from a single vantage point. The better we understand that vantage point, the more truth the data reveals. Measurement is where the story begins. Understanding is where it becomes clear. As cosmologists integrate local cosmic structure into their calculations, the fog around the Hubble tension begins to lift. What once appeared to be competing truths now begins to resolve into a single, more coherent picture. The universe itself has not changed, our ability to read it has. This is the power of precision born from perspective. When the observer's location is treated as part of the data, expansion rates and aligned structures suddenly make sense. Discrepancies reveal real physics instead of artifacts of measurement. What was once a source of frustration is now a powerful diagnostic tool, helping us understand the universe on deeper levels. Cosmology is entering a new era. It is no longer just about collecting numbers, it is about learning to see those numbers in their proper frame, in the context of the universe we actually inhabit. A sharper vision of the cosmos does not mean fewer mysteries. It means that mysteries stand out more clearly against the backdrop of what we finally understand. We have not solved every puzzle, but we can now see the edges of the pieces. For a long time, cosmology chased the farthest reaches of the universe in search of answers. But clarity is not found only at the edge of the observable cosmos. It begins here, in our immediate cosmic environment. By understanding where we are, we finally begin to understand what we are truly looking at. The expansion rates, the background radiation, the large-scale structures we measure, they all carry the subtle fingerprints of our vantage point. When we include it, the puzzle sharpens. When we ignore it, the puzzle fractures. The so-called Hubble tension is one of the clearest ways we see how much our own position in the universe matters. Far from shrinking the cosmos, this insight makes it feel more tangible, more alive. Our local cosmic neighbourhood is not random noise to be ignored. It is the very first layer of the story of everything around us. Without it, our view of the universe is slightly blurred, like a painting half hidden under dust. With it, the vastness of space comes into focus with astonishing clarity. The quest to understand the universe does not begin at the farthest reaches of space. It begins right here, where we stand, on our tiny corner of the cosmic stage. For many years, the Hubble tension has been spoken of as if something in the universe itself had gone wrong, as if the laws of nature had stumbled. Yet the deeper we look at our own position, and how it affects what we see, the more obvious it becomes that the universe was never broken. Our picture was simply incomplete. Every underdensity, every filament, every flow of galaxies is not a flaw in the data, but a vital piece of the scaffolding that shapes the cosmos. Once these elements are included in our models, the contradictions that once puzzled scientists dissolve, and the universe regains its coherence. This is not just about fixing numbers, it is about understanding reality as it truly is. The story of the universe does not need rewriting. It needs to be read again, this time with sharper lenses, brighter light, and a clear sense of where the observer is standing. In the end, the universe remains what it always was: immense, precise, and waiting for us to see it clearly. The Hubble tension is not a tale of failure. It is a story of refinement. Each debate, each recalibration, each correction for the local environment has pushed cosmology to hone its tools. The outcome is not only more accurate numbers, but a deeper understanding of how to measure the universe itself. By embracing the role of our position in these measurements, scientists have reached levels of precision unimaginable only a few decades ago. Modern surveys, sophisticated simulations, and careful study of local structures now allow us to remove noise and see signals with a clarity that was once thought impossible. This transformation will have far-reaching consequences. Every future discovery, from the mysteries of dark energy to the intricate geometry of the cosmic web, will rest upon the foundation built here, on our careful understanding of where we stand. Sharper tools do more than refine old answers. They reveal hidden questions waiting beneath the surface. What was once a source of confusion is now a gateway to discovery. The local structures that once complicated our measurements, underdensities, filaments, and the flows of galaxies, are now essential to the analysis itself. By accounting for them, cosmologists have transformed what once blurred the picture into something that sharpens it. This is a profound change. The very factors that once obscured the Hubble constant may hold the key to unlocking deeper truths about the universe. Environmental modelling does more than correct numbers. It shows how the universe shapes itself, and how it responds to its own architecture. Many scientific breakthroughs come not from finding something entirely new, but from seeing the familiar in a new way. Cosmology today is living in such a moment. The universe itself has not changed. Our way of reading it has. That shift alone opens doors to new understanding. True clarity comes not just from sharper telescopes, but from a better grasp of the view itself. A perfect lens cannot give a perfect picture if the observer does not know where they are standing. By modelling our vantage point carefully, the stubborn Hubble tension has been transformed from a puzzle into a precise scientific instrument. This is the quiet beauty of progress in cosmology. No single discovery solved the problem. Instead, countless small refinements, mapping the cosmic web, modelling underdensities, measuring flows, accumulated until the picture came into focus. Scientific clarity is rarely sudden. It builds slowly, like stars forming in a dark nebula, until the true shape of the universe emerges from the noise. We did not need to look farther into space, we needed to see more clearly right where we are. After decades of chasing discrepancies, cosmology is now learning to observe the universe with newfound clarity. The Hubble tension may not vanish overnight, but it has already reshaped the way science approaches the cosmos. What began as a stubborn mismatch is now the foundation of a more precise and honest understanding of reality. The key was never just bigger telescopes or longer observation campaigns. It was perspective. Once we treated our local environment with all its structures and flows not as noise but as part of the signal, the fog began to lift. Expansion measurements aligned, models gained predictive power, and the universe itself came into sharper focus. This transformation is bigger than a single number. It is a shift in the way we observe, think, and measure. The cosmos has always been here. We are only now learning to see it for what it truly is. A clear universe is not simpler, it is simply more real. Ultimately, the greatest revelation of modern cosmology is not only about what the universe is made of, it is about where we stand within it. The Hubble tension was never just a problem to be solved. It was a reminder that we are not distant observers, but participants in the story we are trying to read. Our local underdensity, the surrounding filaments, and the flows that carry galaxies across space are not footnotes. They are the framework through which the cosmic picture comes into focus. By finally acknowledging that framework, we have turned confusion into clarity and contradiction into insight. Science moves forward not by pretending to be outside the universe, but by accepting that we are inside it, looking out. Every measurement is a sentence in a much larger narrative, and every refinement brings us closer to understanding the plot. The story of the universe was always here. We only needed to realize that we were standing in its pages. The cosmic microwave background is often described as the oldest light in the universe, a faint glow that fills all of space and comes to us from a time when the universe was still very young. Long before stars ignited, before galaxies took shape, and before planets or people could exist, the universe was hot, dense, and filled with energy. As it expanded and cooled, light was finally able to move freely through space. That ancient light has been travelling ever since, stretching and weakening as the universe grew larger. Until today, it appears to us as a gentle background of microwave radiation spread evenly across the sky. This soft glow is not something we see with our eyes, but with sensitive instruments that can detect tiny differences in temperature across the heavens. These differences are incredibly small, often only a fraction of a degree above or below an average value, yet they carry a vast amount of information about the structure and history of the universe. When scientists first measured this background glow, they expected it to be almost perfectly smooth, and to a large extent it is. No matter where one looks in the sky, the temperature of this ancient light is nearly the same. This uniformity tells a powerful story about the early universe, suggesting that it was once in a state of remarkable balance. However, when measurements became more precise, subtle irregularities began to appear. These tiny variations in temperature, often called fluctuations, revealed that the early universe was not completely uniform after all. Some regions were slightly denser, while others were slightly emptier. Over immense spans of time, gravity amplified these small differences, pulling matter together in denser areas to form galaxies and clusters, while leaving other regions more sparse and empty. In this way, the faint patterns in the cosmic microwave background became a kind of blueprint for the large-scale structure of the universe we see today. Among the most intriguing features of the modern universe are vast regions known as cosmic voids. These are enormous stretches of space where very few galaxies exist, sometimes spanning hundreds of millions of light years. Compared to the crowded regions filled with galaxies and clusters, voids appear almost empty, like great bubbles in the cosmic foam. They are not completely devoid of matter, but their density is much lower than average. For a long time, these voids were considered relatively unimportant, mere gaps between the more interesting structures. Yet as scientists have studied them more closely, voids have begun to take on a deeper significance. They are not random absences of matter, but natural outcomes of the way gravity shapes the universe over time. Matter flows out of these underdense regions and into denser ones, making the voids larger and emptier as the universe evolves. The idea that the cosmic microwave background might hold subtle clues connected to these vast empty regions is both fascinating and complex. At first glance, it might seem strange that something formed so early in cosmic history could tell us anything about structures that developed much later. After all, the background radiation comes from a time when the universe was only a few 100,000 years old, while voids formed over billions of years. Yet the universe is a continuous story, and the seeds of later structures were planted very early on. The slight variations in density that appear in the cosmic microwave background are directly related to where matter would eventually gather and where it would thin out. In this sense, voids can be seen as the grown-up versions of some of the cooler, less dense regions hinted at in that ancient light. One way the cosmic microwave background might reflect the presence of emptiness is through subtle temperature anomalies. These anomalies are tiny deviations from the expected temperature pattern, often appearing as slightly cooler or warmer spots on the sky. While many of these features can be explained by random fluctuations or well-understood physical processes, some have sparked curiosity because they seem unusually large or oddly shaped. One famous example is a region often referred to as a cold spot, an area of the sky that appears slightly cooler than its surroundings. This cold spot has been studied intensely, and one idea that has gained attention is that it might be linked to a massive cosmic void lying between us and the distant background radiation. The reasoning behind this idea involves the way light interacts with gravity as it travels through space. As the ancient light of the cosmic microwave background journeys across the universe, it passes through regions of varying density. When it enters a dense region, gravity pulls on it, causing it to lose a bit of energy as it climbs out of the gravitational well. In some cases, the expansion of the universe can change the situation, allowing the light to gain or lose energy depending on how the gravitational landscape evolves while the light is passing through. In the case of a large void, where matter is sparse and gravity is weaker, the effect can be different. Light passing through such an underdense region might experience a slight shift in energy, leading to a small change in temperature when we observe it. This process is subtle and difficult to measure, but over large scales it could leave a detectable imprint on the cosmic microwave background. If a particularly large void lies along our line of sight to a certain patch of the sky, it might slightly cool or warm the background light coming from that direction. The resulting temperature anomaly would be very small, yet with precise instruments and careful analysis, it might stand out from the surrounding pattern. This possibility has driven scientists to compare maps of the cosmic microwave background with maps of the large-scale structure of the universe, looking for correlations between temperature variations and the positions of voids. What makes this search so challenging is the sheer faintness of the signals involved. The temperature differences in the cosmic microwave background are already extremely small, and the additional effect caused by voids is even smaller. Separating this signal from all the other sources of variation requires careful statistical work and a deep understanding of both the early universe and the structures that formed later. It also requires accounting for many other factors that can influence the background radiation, such as the motion of our own galaxy, the presence of interstellar dust, and instrumental effects. Despite these difficulties, the idea that emptiness itself could leave a trace on the oldest light in the universe continues to captivate researchers. The concept of emptiness having an observable effect might seem counterintuitive at first. After all, it is easy to imagine how a massive cluster of galaxies with its strong gravity could influence passing light. It is less obvious how a region defined by the absence of matter could do the same. Yet in the language of physics, a void is not simply nothing. It is a region where the density of matter is lower than average, and this difference still affects the gravitational field. The universe does not measure gravity based on absolute presence or absence, but on contrasts. In that sense, a void can be just as important as a cluster, because it represents a departure from the average state of the cosmos. As scientists think more deeply about the cosmic microwave background and its connection to voids, they are also forced to reconsider how we define and measure emptiness. Voids are not perfectly spherical or uniformly empty. They have complex shapes, boundaries, and internal structures. Some contain thin filaments of galaxies, while others are almost completely barren. Their properties depend on the surrounding environment and the history of matter flow in that region. This complexity makes it harder to predict exactly how a given void should affect passing light. Instead of simple, clear signals, the universe offers subtle hints that must be pieced together like a cosmic puzzle. Another layer of intrigue comes from the fact that the cosmic microwave background is not only a record of density differences, but also of motion. The early universe was filled with tiny flows of matter and energy moving in response to gravity and pressure. These motions left their own imprints on the background radiation, slightly shifting its temperature in different directions. Over time, these early motions evolved into the large-scale flows we see today, with galaxies streaming along filaments and away from voids. In this way, the background radiation and the modern cosmic web are connected not only through density, but through motion as well. This connection suggests that temperature anomalies linked to emptiness might also carry information about how matter has moved over cosmic time. A large void is not static. It grows as matter flows out of it, and its boundaries shift as surrounding structures evolve. Light passing through such a region at different times would experience different conditions. The cosmic microwave background we observe today is a snapshot of how those conditions affected light billions of years ago. By studying these subtle effects, scientists hope to learn not only about the voids themselves, but about the broader forces shaping the universe, including the mysterious influence often called dark energy, which drives the expansion of space. The possibility that voids could help explain certain unusual features in the cosmic microwave background has led to lively debate. Some researchers argue that the observed anomalies are fully consistent with random fluctuations and do not require any special explanation. Others see patterns that seem unlikely to arise by chance alone. The truth may lie somewhere in between, with some anomalies being statistical coincidences and others pointing to real physical connections. The challenge is to gather enough data and develop precise enough models to tell the difference. As new observations improve the resolution and sensitivity of cosmic microwave background maps, the picture becomes richer and more detailed. Tiny temperature differences that were once invisible now come into focus, revealing a delicate tapestry of hot and cold spots spread across the sky. At the same time, large-scale surveys of galaxies are mapping the distribution of matter in unprecedented detail, showing the intricate network of filaments, clusters, and voids that make up the cosmic web. By comparing these two sets of information, scientists can look for alignments, correlations, and patterns that hint at deeper connections. One particularly intriguing aspect of this work is the way it challenges our intuition about cause and effect. The cosmic microwave background originates from a time long before voids fully formed, yet its light has interacted with those voids on its long journey to us. In this sense, the background radiation is both a message from the past and a record of everything it encountered along the way. Each region of space it passed through, dense or empty, left a tiny mark on the light. The final image we observe is a layered story, combining information from the early universe with the imprint of later cosmic evolution. This layered nature makes the background radiation a powerful but complex tool. Interpreting it requires disentangling signals from different eras and processes. Temperature anomalies linked to emptiness are not standalone features that can be read in isolation. They are part of a broader pattern that includes the original fluctuations from the early universe, the effects of cosmic expansion, and the influence of intervening structures. Understanding one piece of this pattern often requires understanding all the others as well. The idea that emptiness might speak through subtle temperature changes also has a philosophical resonance. It suggests that even the most seemingly insignificant aspects of the universe, the places where little appears to be happening, can play a role in the grand cosmic story. Voids are not just empty gaps between important structures, they are active participants in the evolution of the universe. Their growth, shape, and distribution influence how matter moves and how light travels. In this view, emptiness becomes a source of information rather than an absence of it. As researchers continue to explore these ideas, they develop more refined ways to describe and measure voids. Instead of treating all voids as the same, they classify them by size, shape, and environment. Some voids are surrounded by dense walls of galaxies, while others are more gently defined. These differences may affect how strongly a void influences passing light. By studying large samples of voids and averaging their effects, scientists hope to tease out a clearer signal from the background radiation. At the same time, the study of temperature anomalies encourages a deeper look at the assumptions built into cosmological models. The standard picture of the universe has been remarkably successful in explaining a wide range of observations, from the abundance of light elements to the large-scale distribution of galaxies. Yet small tensions and anomalies remain, hinting that the story may not be complete. The interaction between the cosmic microwave background and cosmic voids is one area where new physics could potentially reveal itself, not through dramatic deviations, but through gentle, almost whisper-like effects. These whispers are easy to miss, drowned out by noise and uncertainty. But with patience and careful analysis, they may offer insights into how gravity works on the larger scales, how the expansion of the universe has changed over time, and how structure emerged from near-uniform beginnings. Each tiny temperature anomaly becomes a clue, a faint mark left by the universe as it evolved from a hot, smooth state into the richly structured cosmos we inhabit today. The exploration of these ideas also highlights the collaborative nature of modern science. Understanding the connection between the cosmic microwave background and voids requires expertise from many areas, including observational astronomy, theoretical physics, data analysis, and computer simulation. Large teams work together to design instruments, collect data, and test models against observations. The resulting picture is built gradually, with each study adding a small piece to the overall understanding. In this ongoing effort, the role of emptiness continues to grow in importance. What was once ignored or simplified is now examined in detail. Voids are recognized as key elements of the cosmic web, shaping the flow of matter and the path of light. Their influence on the cosmic microwave background may be subtle, but it's part of a larger realization that the universe is interconnected in ways that are not always obvious. Light from the dawn of time carries with it the memory of everything it has encountered, including vast regions where matter is scarce. The study of subtle temperature anomalies linked to emptiness also encourages a sense of humility. The effects being sought are so small that they challenge the limits of measurement and understanding. They remind us that the universe often reveals its secrets not through dramatic displays, but through delicate patterns that require careful attention to notice. In learning to read these patterns, scientists refine their tools and deepen their appreciation for the complexity of the cosmos. As observations continue and theories evolve, the dialogue between the cosmic microwave background and the voids of the universe remains open. Each new map of the sky, each new catalogue of galaxies, adds depth to this conversation. The background radiation continues to glow softly, carrying its ancient message, while the vast empty regions between galaxies quietly shape the journey of that light. Together, they form a story that stretches across billions of years, linking the earliest moments of the universe to its present-day structure in a subtle and intricate way. Mapping the Cosmic Whole is a story about how human curiosity slowly learned to see emptiness not as nothing, but as something deeply meaningful. For a very long time, when people looked up at the night sky, they focused only on the bright points of light. Stars, planets, glowing clouds, and later entire galaxies were the heroes of the cosmic story. Darkness was treated as background, a blank stage on which the actors performed. Yet modern astronomy has revealed that the dark spaces between galaxies, the vast regions where very little seems to exist, are not random gaps. They are part of a grand structure, shaped by gravity, time, and the slow unfolding of the universe itself. These enormous empty regions are often called cosmic voids, and together with long threads of galaxies known as filaments, they form what scientists describe as the cosmic web. Mapping this web, including its holes and strands, has become one of the most fascinating projects in modern science. To understand how these maps are made, it helps to imagine the universe not as a flat picture, but as a deep, layered space. Every galaxy is not only positioned somewhere across the sky, but also at a certain distance from us. This distance tells us how far back in time we are seeing it, because light takes time to travel. When astronomers collect light from millions of galaxies, they are really collecting pieces of a three-dimensional puzzle that stretches across space and time. Modern galaxy surveys are the tools that gather these pieces. They are vast projects that use powerful telescopes, sensitive cameras, and careful measurements to record where galaxies are and how they move. One of the most important techniques used in these surveys is the measurement of redshift. When a galaxy is moving away from us, the light it sends becomes stretched, shifting toward the red end of the spectrum. By measuring how much this light has shifted, astronomers can estimate how fast the galaxy is moving away and how far it is from us. This turns the sky into a kind of depth map. Instead of seeing galaxies as dots on a flat surface, scientists can place them at different distances, creating a three-dimensional view of the universe. When this is done for hundreds of thousands or even millions of galaxies, patterns begin to emerge. At first glance, these patterns can look chaotic. Galaxies appear clumped in some areas and sparse in others, but as the maps grow larger and more detailed, a clear structure becomes visible. Galaxies are not spread evenly through space. They gather along long, thin filaments that stretch for immense distances. These filaments intersect at dense regions called clusters, where hundreds or thousands of galaxies are bound together by gravity. Between these bright strands and knots lie enormous regions where very few galaxies are found. These are the cosmic voids, the so-called cosmic holes that can span tens or even hundreds of millions of light-years across. Mapping these voids is not as simple as pointing a telescope at an empty patch of sky. Emptiness does not shine. Instead, astronomers must infer the presence of a void by carefully studying where galaxies are not. This requires surveys that are both wide and deep. A wide survey covers a large area of the sky, while a deep survey looks far into space and time. Combining both allows scientists to see the full shape of the cosmic web, including its holes. Modern galaxy surveys use advanced instruments that can observe many galaxies at once. Some telescopes are equipped with devices that can take spectra of thousands of galaxies in a single night. Each spectrum provides information about the galaxy's distance, motion, and sometimes its composition. By repeating this process night after night, and year after year, astronomers build enormous catalogues of galaxy positions. These catalogues are then fed into powerful computers that reconstruct the three-dimensional structure of the universe. Once the data is collected, the challenge becomes identifying the voids and filaments within it. This is where modern computational techniques play a crucial role. Scientists use algorithms that search for regions with very low galaxy density. Imagine pouring sand onto a surface and watching how it naturally forms ridges and valleys. In a similar way, when galaxies are plotted in 3 dimensions, some regions rise with high density while others sink into emptiness. Algorithms trace these valleys to outline the voids and trace the ridges to follow the filaments. Some methods treat the galaxy distribution like a fluid, flowing from dense regions into empty ones. By studying how this imagined flow behaves, scientists can locate the boundaries of voids. Other methods use mathematical shapes, building networks of connections between nearby galaxies. Where connections are sparse or missing, a void is likely present. Each method offers a slightly different view, but together they build a rich picture of the cosmic web. What makes these maps especially interesting is that voids are not simply empty bubbles. They have structures of their own. Inside a void, there may be a few lonely galaxies, often smaller and less evolved than those found in dense regions. The edges of voids are particularly important, as they are where filaments form and where galaxies feel the pull of surrounding matter. By mapping voids in 3 dimensions, astronomers can study how galaxies change depending on their environment, offering clues about how matter behaves on the larger scales. Another powerful technique in modern surveys involves using the faint glow left over from the early universe as a background light source. As this ancient light passes through space, it is subtly affected by the distribution of matter. Even voids leave their mark by allowing light to travel slightly differently compared to dense regions. By combining galaxy maps with studies of this background light, scientists can cross-check their maps and refine the shapes of voids and filaments. Gravitational effects also play a role in mapping the cosmic web. Massive structures like clusters and filaments can bend light from distant galaxies, creating small distortions known as gravitational lensing. By measuring these distortions across large areas of the sky, astronomers can map the distribution of matter, including matter that does not shine at all. This technique is especially useful for studying voids, because it can reveal how truly empty they are and how matter is distributed around them. As surveys become more detailed, they also become more complex. Observational limits such as dust in our own galaxy, or the faintness of distant galaxies, can create gaps in the data. Scientists must carefully correct for these effects to avoid mistaking observational holes for real cosmic voids. This requires detailed simulations, where virtual universes are created based on known physical laws. By comparing real data with simulated data, astronomers can test their methods and improve their maps. 3-dimensional mapping has revealed that voids come in many shapes and sizes. Some are nearly spherical, while others are elongated or irregular. They can merge with neighbouring voids, creating larger empty regions over time. Filaments, on the other hand, can twist and branch like the roots of a giant tree. Mapping these shapes helps scientists understand how the universe grew from its early, nearly uniform state into the richly structured cosmos we see today. The idea of a cosmic hole may sound like something missing, but in many ways, voids are just as important as the galaxies themselves. They occupy most of the volume of the universe. While galaxies and clusters contain most of the visible matter, voids dominate the space between them. Mapping this space is essential for understanding the overall geometry and behaviour of the universe. Modern techniques also allow astronomers to study how voids affect the motion of galaxies. Galaxies are not only pulled toward dense regions, but also pushed away from voids. This gentle push shapes the flow of matter across cosmic scales. By measuring galaxy velocities and comparing them with the locations of voids and filaments, scientists can test theories of gravity and cosmic expansion. Another fascinating aspect of void mapping is how it connects the present universe to its earliest moments. The patterns seen in today's cosmic web grew from tiny differences in density that existed when the universe was very young. Over time, gravity amplified these differences, drawing matter into filaments and leaving behind empty regions. By carefully mapping voids, astronomers can work backward, tracing how these structures evolved. This makes voids a kind of fossil record, preserving information about the universe's past. Large surveys continue to push the boundaries of what can be mapped. New instruments are designed to observe fainter galaxies and cover larger volumes of space. As a result, maps of the cosmic web are becoming more complete and more detailed. These maps are not static pictures but living data sets that grow richer as more observations are added. Each new galaxy placed in three-dimensional space sharpens the outlines of filaments and deepens the hollows of voids. The process of turning raw telescope data into a map of cosmic holes is both technical and imaginative. It requires precise measurements, careful corrections, and creative ways of visualizing immense structures that no human can see directly. Scientists often use color, transparency, and motion in computer visualizations to help convey the depth and scale of the cosmic web. These visual tools not only aid research, but also help share the wonder of these discoveries with the wider world. Mapping voids also changes how we think about emptiness itself. In everyday life, empty space is often seen as unimportant. In the universe, however, empty regions shape the paths of galaxies and the flow of matter. They influence how structures grow and how light travels across vast distances. By studying voids, scientists learn that absence can be as powerful as presence. As techniques improve, researchers are beginning to study smaller and subtler voids, as well as the fine details of filament structure. This includes examining how gas flows along filaments into galaxies, fueling star formation, and how the quiet environments inside voids lead to different kinds of galaxies. Each of these studies adds another layer to the map, making it not just a chart of positions, but a story of movement, growth, and change. The cosmic web, with its holes and strands, is one of the largest patterns ever discovered by humanity. Mapping it in 3 dimensions is a triumph of collaboration, technology, and patience. Thousands of scientists, engineers, and students contribute to these surveys, often working across continents and decades. Their combined efforts turn faint points of light into a detailed picture of the universe's structure. As maps grow more precise, they also raise new questions. Why do voids have the sizes and shapes they do? How do they interact with the mysterious components of the universe that cannot be seen directly? How does the presence of vast empty regions influence the overall behavior of cosmic expansion? Each question leads to deeper exploration and more refined mapping techniques. The act of mapping the cosmic whole is therefore not just about filling in blanks. It is about recognizing patterns in absence, about seeing structure where once there seemed to be nothing. Through modern galaxy surveys and 3-dimensional mapping, the universe reveals itself as a connected whole, where light and darkness, matter and emptiness are woven together into a single, vast tapestry that stretches beyond imagination and continues to invite closer inspection.